Okay, everybody, please take your seats. Just to let you know, there is electrical plugs in the center of row 1 and row 6. Otherwise, also, there's a couple of extension cords and connectivity on the sides. Aviv? Gil, all good? Okay. Good morning. Boker Tov. Burim Habraim L'Israel. Welcome to Israel. My name is Anton Yemelyanov. I'm chair of the Scaling Bitcoin Planning Committee, one of the organizers of these events. Aviv Zohar is the chair of this conference. I'd like to give you words to explain the meaning or the theme of this conference. So, Bitcoin deliberately prioritizes the characteristic of digital sound money. Its architecture, engineering, practice, and economic design all optimized for that objective. Its total monetary supply is fixed, and the monetary issuance algorithms are relatively simple, transparent, and rooted in physical world. Its architectural choices prioritize simple elegance, security, decentralization, failure resistance, and de-risking of the base layer over performance, throughput, and features. Development is methodical, systematic, meticulous, and conservative. There are the engineering constraints that the commitment to sound money imposes. Bitcoin's progress can appear slow as a result. But in mission-critical systems, avoiding making mistakes that result in systemic harm is more valuable than developing features quickly or goosing performance numbers. In fact, that alone is an extremely difficult engineering challenge. Perhaps Bitcoin is more like a swimming duck, making calm and steady headway, but with feet spinning madly under the water. Within the broader cryptocurrency ecosystem, there needs to be at least one such high conservative cryptocurrency dedicated to principles of sound money. And others can be more experimental to varying degrees. Some will prove useful and advance the state-of-art cryptography, distributed systems, and other aspects of cryptocurrency. But Bitcoin's role is the trust anchor for that system, and the fallback in case of systemic failure of other parts of crypto economy. It is the foundation. It is the Yesod. So Yesod means foundation in Hebrew. Its unique constraints, seemingly slow pace, and engineering and economic conservatism are what enables it to serve that role. I'd like to remind everybody that scaling Bitcoin is run under a very strict code of conduct. We don't allow any photography or videography at the event, and the event is run under Chatham House Rule, which means the information is on the website, but it basically means that you can quote what has been said at this conference, but you're not allowed to quote who said something. With that, I'll pass the mic to Aviv Zohar, the chair of this conference, professor at Hebrew University.
Thank you. All right. So, Anton, one correction. I think it is okay to take pictures of people on the stage, right? Yeah, because this is being streamed.
Yeah, everybody, the presenters are on the live stream, so that's obviously
okay. So that's fine. Hello, everybody. Welcome to Tel Aviv. It's a great pleasure to have you all here. This conference has a lot of history in some tumultuous times as well. If people who have been going to it for a while probably remember. If I'll take Anton's image of Bitcoin as the duck swimming in the water, there's usually a storm out there. But the duck has been swimming pretty consistently and in a nice and straight line. I think we should maybe start, all of us, by really giving a great big thanks to Anton for pushing to get this conference moving around from place to place, doing a lot of hard work. It wasn't easy. There's a lot of politicking and navigating and fundraising and logistics involved in running a conference like this. Maybe the second person to thank in this case is Jonathan, who's sitting right here. We're soon going to hand over running the event to him. He's been running the program committee and has been filtering the talks that you're going to see. There's, I think, what turns out to be a great lineup of speakers, and it's going to be, I think, a wonderful 2 days ahead of us. So, Jonathan, do you want to say a few words about the process?
Yeah, sure. Not much to say.
Maybe before that, just hand of applause to Anton, local organizer. Thank you.
Hey all, just give some visibility into the process. There's other blockchain Bitcoin conference around, and so it's not always clear to people how talks are selected. So this is a more academic venue. The talk, we assembled a program committee. You can see the members online on the website, some of which are here. And basically, in case you're not familiar, it's a double-blind review. People submit, and reviewers, grade it according to several vectors. So that's just on the general process. We try to be as fair as possible and as blind as possible to the extent it's possible. If someone, for instance, submitted a work that everyone knows they are associated with, so there's nothing to do about that, but that's also, part of the academic game. We try to balance between things that are applicable to Bitcoin today, as on a BIP level, versus things that are more Bitcoin in a few years or hypothetically in Bitcoin, things that will interest the Bitcoin community that they are part of the technical narrative. So in case you are wondering what's the scope, it's Bitcoin focused with some navigation between immediately applicable to Bitcoin and just something that the reviewers felt that it is part of the Bitcoin's narrative. Anything else? Okay, we got 44 submissions roughly, and 25 will be submitted, were accepted at the conference. We'll hear some WIPs, work in progress, tomorrow. So you'll get a notion of what people are working on, other than like more half-baked ideas and works in progress. Yeah, okay.
All right, maybe one more thing I forgot to say. We should also thank some of our sponsors who helped us have this event and also supported events that came earlier in the week. I think this is part of the theme of scaling Bitcoin. We started out this week with a workshop on regulation. It was interesting to see Bitcoin maximalists meet regulators in the same room. An interesting experience, I assure you. And then the Dev++ workshop that's running under Edge. So this is separate from the conference, but still this is some way of scaling up the development community around Bitcoin. So I think we'll start with the program and end all these formalities. So I'd like to invite Ben Fish to give us a first talk. Ben's going to be talking, this is an invited talk, which is a survey on progress in succinct zero-knowledge proofs towards trustless snarks.
Thank you, Aviv.
This is your time.
Okay,
And
that's not my talk.
that's your talk. Does he need the lavalier?
better quality.
Okay.
אז זה כאילו רק
We don't want to dim the light. Gil, we don't want to dim the lights, no? Because we want to see the speaker and you're streaming the separate machine. There's no need to dim the lights because the streaming is, they'll be able to see the,
Okay. What?
אתה תצטרך בכל מקרה מיקרופון רגיל גם.
What? I didn't
זה בשביל המצלמה, ואחד בשביל האולם.
Oh, okay. Got it. Got it. Ah, I understand.
oh, we need to look. Just 1 second. Yeah, are you still okay? You see this on streaming? Okay. So this is your countdown. You have 25 and 5 minutes queue.
Great. Thank you. Should we?
This is the clicker.
Yeah. Is this going to go away or?
However,
Maybe just cancel. Okay, perfect. Great.
you can use this. Or
No, I think that one is for the video, one is. Okay, hello. So I'm going to give a survey of progress, recent progress in succinct zero-knowledge proofs. But here are my talk goals. So first, I will survey recent developments, but I'm going to start with, since I don't know that everyone necessarily, and I think this is helpful for being able to keep up with SNARK progress, present a kind of a unified view, starting a little bit with the history of underlying paradigms and techniques, which really helps to categorize in your mind what's happening with SNARK. So otherwise, it can seem like there's an explosion of different papers, and it's hard to keep track. One theme is the emergence of polynomial commitment schemes as an extraordinarily key tool towards building efficient SNARKs that are transparent, that do not involve a trusted setup. And lastly, at the end, I will announce a new trustless polynomial commitment scheme that is based on fresh work that I'll be posting with my co-authors, Benedict and Alan, in a few days. And the result of that, as you will see through the talk, is the ability to build trustless SNARKs. So, what is a zero-knowledge SNARK? A zero-knowledge SNARK is a zero-knowledge, succinct, non-interactive argument of knowledge. And the relevance of SNARKs, especially to, say, the Bitcoin community, is as both as a scaling technique. It can be used to verifiably outsource computations, as well as a key scalability tool for privacy. Because zero-knowledge proofs are a kind of proof, and when you're doing zero-knowledge proofs on large statements, then SNARKs are what allow you to produce a small proof that can be put on the blockchain, even if you're proving a large statement. So, for example, anonymous transactions in Zcash, which currently the Bitcoin community somewhat shuns for requiring a SNARK with a trusted setup, would be more welcome if there were a way of doing it without trusted setup. So what is a SNARK? So it is a non-interactive proof. So there's a prover who sends just one message to a verifier, and it proves abstractly, it can prove anything which is a relation that can be computed by a polynomial size, or in other words, efficient circuit. So this is called the class of NP. And so if I have a statement and a witness, such as, here's an encrypted confidential transaction, and here's the witness, which is the secret information that you would need if you were going to verify this in the clear, then you can verify my proof instead, that if you had the private information, you would be able to verify that this statement is true. And Succinct says that the proof is small. For example, polylogarithmic, although you could define more flexibly to be square root or something like that, in the size of the circuit that computes this statement in the first place. And in particular, that means that it is succinct in the size of the secret information. So if I have a long secret information, instead of sending it to you in the clear, I can just prove that I have it. And efficiency states that the verifier time similarly is efficient. So even if you're proving a very large statement, the verifier can do only a small amount of work to verify that. For example, polylogarithmic in the circuit size. And knowledge extraction says informally that basically if the prover succeeds in convincing the verifier of this statement, then the prover actually knows that extra secret information that was needed to that makes the statement true, right? And so this is a very strong security or soundness property that implies that the statement is correct as well, but it shows even more. It shows that the prover actually knows the secret information that makes this statement true. And zero knowledge says that basically the interaction, or in other words, the proof, doesn't reveal anything about that secret information. So what do we mean by transparent setup? Well, sitting on the slide has been this setup procedure at the top. And so it's there because some snarks, and in fact, snarks, all efficient snarks really today, involve some kind of setup of public parameters. And the setup is called transparent if it involves no secret. So anybody can verify that that setup was done correctly. This is a publicly verifiable setup. One thing that's missing from this picture here, and I can talk a little bit about later when we talk about ways people construct these things, is pre-processing snarks. So maybe the verifier needs to, in order to be able to trust the system in a trustless way, for any given circuit that is, or new statement that's being proved, needs to, at one time, do a large amount of work to verify that some pre-processing has been done correctly, but then later, when verifying even multiple instances of the same statement, would not need to do so much work. So we'd still get a succinct or efficient verification. So let's now talk about where snarks began. So in the beginning there was nothing, and then there was the PCP theorem, which is one of the crown jewels of computer science. In the Hebrew year 750, I think, and 1990, Ben Fish was born. And also the first version of the PCP theorem, which said that any exponentially long proof could actually be verified using just a polynomial amount of randomness and checking only polynomial number of locations. And lots of progress involving lots of people eventually got to the celebrated PCP theorem as we know it, which says that any polynomial size proof, so like proof that I could give you efficiently, can actually be checked on only a constant number of locations using a log n amount of randomness. So what does the PCP theorem really say? It says that basically anything that I would want to prove to you, I could give to you, and if you had random access to that proof, so in a model where you basically have oracle access to the proof, and reading a single bit of the proof is just a order 1 operation, then you only need to do a constant amount of work to verify this proof. And you only need to look up a constant amount of locations. So CS proofs were the first step towards snarks as we know it. These were computationally sound proofs, and the idea was, building a work of Killian and then Micheli, was to commit to this PCP proof with a Merkle tree, and then when the verifier wants to look up some locations in the proof, the prover can simply give Merkle proofs that they're reading the correct location. So the prover would tell the verifier what location, what the answer to the query to that location is, and give a Merkle proof to show that that was correct. And then that can be made non-interactive with this thing called the Fiat-Shamir transform. So pictorially, the interactive version would be the prover sends the Merkle tree root, then the verifier sends basically the random challenges of where they want to check the proof, and then the prover would provide Merkle proofs for the query locations. But that can be made non-interactive by setting the random challenge that the verifier would send based on a hash applied to the first messages in the interactive transcript. And so this paradigm actually will appear over and over again, and we can look at all constructions of snarks as taking an information theoretic proof system and applying some kind of cryptographic compiler to that in order to turn it into something which has the properties of a snark. So in this case, we took an information theoretic interactive proof based on this restricted model of oracle access to a PCP, and we applied Merkle trees and random oracle hashes and this Fiat-Shamir transform in order to turn it into a snark. So the next question was, well, okay, are there other kinds of PCPs which maybe provide a bit more power than just being able to check individual locations of a proof? So let's say that the PCP is actually a function. So the prover would send to the verifier a vector, and then let's say that the verifier somehow had the ability to make queries that return inner products of that vector with the query. Now, this is called a linear PCP, and indeed, one of another stepping stone towards the efficient snarks that we have today was a result by Ishai Kushilevitz and Ostrowski, which showed a 4-move linear PCP based on Hadamard code, and then gave this different kind of cryptographic compilation that's not like Merkle trees, but uses a bit more powerful techniques. They use linear homomorphic encryption in order to turn that into a snark. Unfortunately, this initial work had linear verification time and quadratic proving time, but it was a stepping stone towards seminal work of GGPR, who gave another type of linear PCP based on these quadratic arithmetic programs. Many of us might be familiar with these instead as rank 1 constraint systems, which I'll mention in a couple slides, very similar to QAPs. And this was developed further in many, many follow-up works. And what is the underlying technique in QAPs? Well, there's QAP-based linear PCP, so it is exactly following this idea of designing an information theoretic protocol where the verifier just makes inner product queries to some vector that the prover has. And that's compiled using something called linear-only encodings. And because of the properties of the QAP, they were able to get down to n-log n proving time and constant verification. So giving the example of an R1 CS constraint system, which is a sort of a further simplification of QAPs, basically there's a bunch of polynomial matrices, and the witness, the secret witness, which the first L bits of the witness may be the input, and you just need to show that the circuit will be satisfied if this constraint equation is satisfied. And you can see it's basically matrix vector operations, except for h of x times z of x, and as well, since these are matrices of polynomial, it's not quite yet a totally linear operation. It's operations on matrices of polynomials. But the way this is converted into a linear PCP is by choosing a random point, evaluating the polynomials at the random point. So then you get actual matrices, and making a whole basically just 5 inner product queries, and then doing some quadratic check on the results. This is what the R1CS linear PCP looks like, and the way that that is then used to produce a pre-processing snark is by pushing these the secret queries that would normally be made by the verifier into some pre-processing step, so that this hidden random alpha is chosen by a trusted setup, and it's compiled into a snark by using this, again, linear-only encoding to force the prover to actually apply those queries to the witness vector that they commit to. But this approach appears to fundamentally require this trusted non-universal setup. Non-universal means for every circuit, when the queries change, basically you have to do a new trusted setup to push everything into the pre-processing. So, meanwhile, going back to the original Micheli proofs that were just based on classical PCPs, there was interesting work going on of making that original approach of these weaker PCPs more practical. The problem was the original PCPs were beautiful in theory, but not in practice. And so we had introduced the notion of interactive oracle proofs simultaneously by Rangel et al. And by Ben Sasson et al. They noticed that, well, you can get a lot more power if you allow interaction, so that there's multiple rounds of interaction, and in every round the prover will send some proof oracle that then or PCP that the verifier then just is able to check via random access in a few locations. And if you were to apply cryptographic compilation techniques to that, then you'd get a multi-round public coin protocol involving Merkle trees, and that could be compiled into a snark, as we saw before. So multiple rounds allow for much greater efficiency, and there's a whole bunch of works that do this. And another nice thing is that these weaker PCPs, the compilation techniques are also very basic, using things like Merkle trees and hash functions, compared to linear PCPs, which involve more complicated, heavyweight cryptography. So they tend to be more, maybe not as efficient in terms of proof size, but more efficient in terms of the actual operations and work that's being done. So two state-of-the-art results in this line of work are Starks and Aurora, and each of these have seen, I guess, further developments that I'm not citing here. But basically, Starks work for uniform programs, many repetitions of a small unit of a program that are being done many times over, and Aurora is more for general circuits. Both have log squared size proofs, or arguments that are then compiled into proofs, and Starks have sublinear verification, but only for uniform programs, which Aurora would have as well. Aurora, unfortunately, has linear verification time, so is not quite a snark under all definitions yet. So the natural next question is, well, what about allowing interaction for the more powerful PCPs? Like linear PCPs. Like the QAP was not really interactive, but what if we allowed for multiple rounds of interaction where there's multiple rounds of challenges from the verifier, and in each round the prover is sending some commitment to a vector that the verifier then can make linear queries to. So we would call these linear interactive oracle proofs. And one special case of a linear interactive oracle proof would be just a polynomial. So let's say that the proof is a degree d mu-variate polynomial, and the verifier query is just the evaluation of that polynomial at a point. So the information theoretic protocol would be sending polynomials. The verifier wouldn't have to read the whole polynomial, but would somehow have oracle access to receiving that polynomial evaluated at a point. if you want to allow coordinate queries like reading coefficients of the polynomial, which are similar to the point queries of the classical PCPs, there's a generic reduction that replaces a coordinate query with a 2-round polynomial interactive oracle proof. So, polynomial PCPs kind of sit between linear PCPs and point PCPs. They actually seem pretty close to point PCPs because if you think about it, the polynomial can be represented as a short PCP as well. And there's actually, a lot of the modern work in point PCPs, use polynomials as well in the way that they actually work. So the general paradigm which has emerged in a lot of the recent works is actually compiling polynomial IOPs using something called a polynomial commitment scheme, which I will explain in the next slide. But the process is to take the polynomial IOP. Every time the prover would send a polynomial to the verifier, we send instead a polynomial commitment, and that's then applied as a compiler to turn this into an interactive argument that doesn't involve these oracles, and then it can be compiled into a snark using the usual Fiat-Shamir trick. So what's a polynomial commitment scheme? It works like a normal cryptographic commitment scheme. First of all, there's a setup, there's a commitment, there's an opening. This commits to the polynomial as a message. But then the key new thing is an interactive protocol which allows you to prove that the polynomial evaluated at a point is equal to some claimed value. Say f of z is equal to y, and the efficiency requirement is that this interactive protocol should have communication which is sublinear in the size of the polynomial. Otherwise, you could just send the polynomial, right? And the commitment should also be small. Like ideally, Compton size or really order of the security parameter. Say a single group element if you're using groups for the commitment. And it would be also nice if the interactive protocol is public coin, because then it can be transformed into a non-interactive protocol. So the security properties are that you shouldn't be able to open the polynomial to two different values at the same point, evaluation binding. And argument of knowledge would be nice as well, showing that if you have successfully evaluated this polynomial and gave a proof that you evaluated it correctly, then you actually know the polynomial. So a transparent setup would be just as before, involving some setup which doesn't have secrets. And the previous state-of-the-art construction by Kate et al. From bilinear groups does have a trusted setup. In fact, a large trusted setup which produces powers of some secret value s up to the degree of the polynomial. And so that has to be done by some trusted party or an MPC. And so the first result that I'll mention, which is a recent result, Sonic, the theorem wasn't exactly stated in this way, but this is the underlying result in that paper. It shows how you do, and based on previous work as well, a polynomial interactive oracle proof for any NP relation that makes just one bivariate query and three univariate queries of the degree, size of the circuit polynomials, and it's 2 rounds. And that can be transformed into a 5-round protocol with 24 overall univariate queries. And so if you were to just apply out of the box the Kate et al. Commitment scheme, then you get a snark which has just one-time universal setup to establish this trusted setup for that commitment scheme, and it can be compiled in the way I described previously to turn this information theoretic polynomial oracle protocol into a standard interactive protocol, which then transforms into a snark. So in the special case of uniform circuits, the bivariate polynomial can just be evaluated by the verifier itself efficiently, and so you end up with a much more efficient 2-round IOP with just 3 univariate degree CR queries. So it does give you this universal setup, as I just mentioned, as well as linear time preprocessing per circuit. So I don't really have time to talk about this in detail, but I want to mention, so a lot of these other, line of other works are based on this sum check protocol. This is a very, very classical protocol, also from the 90s. And don't worry about the details of the protocol, but I just want to mention that you can also think of this protocol as a polynomial IOP as well, because in every round, basically, the prover is sending a polynomial, and the verifier is doing a few checks, and then at the end, evaluates this polynomial at a random vector. And so you can look at these as polynomial PCP oracles, and then making some oracle queries. And so this GKR interactive proof, which is the basis of a whole other line of SNARK works by defining a polynomial at each level of the circuit, which basically just says that A of Z says that this is an addition gate. If this is an addition gate, then if the V represents the output of that gate, so you just add the two, or the input to that gate, so you add the two values, and if it is a multiplication gate, then you multiply them. And so it kind of has this recursive definition of what a polynomial that kind of encodes each layer of the circuit, and each of these can then be replaced with a sum check protocol, which is done kind of recursively, and what you end up with is order of D log C rounds, where D is the depth of the circuit. So it can be done efficiently if you have a low depth circuit, and all the queries are on low degree polynomials, so it actually doesn't need polynomial commitments. They can just be read entirely in the clear. So, and that has to do with the way that it was defined. Those polynomials just turn out to be very low degree polynomials, so you don't actually need the machinery I was discussing before. But improvements to GKR, since GKR is not zero knowledge, tried to make GKR zero knowledge by doing things like adding small random masking polynomials. And so this is recent work of Libra, and also Hyrax as well does similar things with using techniques. And so both of these things end up involving polynomial commitments as well, in order to, because they get larger degree polynomials than what GKR normally just has. Hyrax also has a polynomial commitment scheme with no trusted setup, but it had square root size proofs. So it's not a really succinct SNARK with logarithmic size proofs. So then finally Spartan, and my time is up, I'm almost done. So Spartan used, and this is building on previous work of Clover, and actually goes all the way back to BFL 91. You can represent the satisfiability of an arithmetic circuit using this sum over all values in this Boolean hypercube of this polynomial G. And so what you get from Spartan is basically a theorem that there exists an interactive oracle proof, a polynomial interactive oracle proof, that involves a logarithmic number of rounds, but really just 3 queries to a log C variate polynomial oracle, and 1 query to each of those to 3 log C variate polynomial oracles. And for uniform circuits, you really just you don't need to make queries to the 3 log C variate polynomial oracles, which is important for efficiency, and you just need to make 3 queries to the log C variable polynomial, which using previous work can be done with square root size proofs and linear proof of time. So this is, I just took this straight out of Libra, which is sort of a comparison of different sizes that have been reported, as well as running times. You can see all the way down from the most efficient SNARKs, which rely on a heavy trusted setup, which are much less than a kilobyte, to the ones that are based on classical IOPs, which are closer to the 400 kilobyte range, as well as things in the middle. So finally, I'll announce that there's new work by myself and Benedict Bunz and Alan Speniak, who's here in the audience. And we have a polynomial commitment scheme from groups of unknown order. And if you instantiate that with class groups, then you get a polynomial commitment scheme that has transparent setup, constant size commitments, and order log D evaluation openings. And what that means is that if you apply it, say, for example, to Sonic, we get what we call supersonic. And it's a trustless setup SNARK with log n size proofs and log n verification, quasi-linear proof of time, and pre-processing as well. So an estimate would be about 24 kilobyte proof sizes for 1,000,000 gate circuits, although further optimizations are possible, so you can kind of see where that fits in on this chart. So it's not as good as, say, what you get from using libsnark, but it's currently better than the state-of-the-art for the other trustless setup snarks. So Alan will be talking about that next week. You should attend his talk if you're still around at Starkware sessions. So thank you. I conclude with that. Yeah. Is there any questions? Yes.
Yeah. How does Halo from Electric Coin, Zcash, fit into this?
Great. Yeah, great question. The question was about Halo from Zcash, which was announced just 2 days ago, so I didn't quite have the time to, fully learn about the result. But in discussing it with colleagues, as well as my colleague Benedict discussed with Sean as well, the claim is a bit more refined. It's not a snark. It's not a trustless setup snark. What it is, it's an amortization technique that allows you to take many snark proofs, and you still need to do linear work to verify in the size of the statement. But if you have a lot of proofs that you're verifying at once, then also in the specialized setting with a helper, you can amortize the cost of that and just do it at the cost of verifying one proof. So what they apply it to is getting efficient recursive composition of snarks, which is relevant for some applications. And it's relevant, I would say, in the blockchain setting because the miner is a natural party to be a helper. But it does not give you a snark, which would be something where if you're proving a fresh statement, then you can verify it in log n work, and the size of the proof is just log n. It's not a snark in that sense. Yeah. Any other questions? Okay, thank you very much.
So our next speaker is Omer Shlomovitz. He's going to be talking about threshold scriptless scripts. I'll let him set up for a bit.
Just anybody needs Wi-Fi. It's a free tau, and then the password is lowercase free-tau.
Free-tau is the lowercase is the password, and the network is free tau. Is it? Yeah.
This is the clicker if you need. There we go. Your time. This is your time. You have, but this is the counter. Okay. You have 25, and then 5 minutes will be on.
Okay. So hi everyone. My name is Omer from Kaizen. I'm going to talk about scriptless scripts, and starting from shamelessly copying a new post definition. So we can write smart contracts in Bitcoin today, but and it's fantastic because we can do many things with it, many great things. We can use it for atomic swaps, for payment channels, for multi-signatures, and so on. But there is a cost. So the transactions are becoming bigger. The chain it requires more space on chain, and also it's kind of heavy on verifiers, right? Because they, in uncompressed way, need to verify more things. So and there's also a privacy issue because you basically put your contract publicly on chain. So to solve this, we want to achieve the same functionality, but without actually using smart contracts. So just based on regular transactions like public, and just using the primitives of public keys and signatures. So I'm going to introduce scriptless scripts using Schnorr signatures, which was the way that they were originally described. And then we'll ask the question, so Schnorr is not yet supported in Bitcoin, but we want to get to do it like today. So how can we do it with ECDSA, which is the signature scheme that is used in Bitcoin, and it will require us to ask few hard questions. So why ECDSA is different than Schnorr? Maybe there's something inherent to ECDSA that wouldn't allow us to do it. And once we get done with this and rebuttal some known issues, we'll need to discuss and enlarge our toolbox. So it's mainly going to be tools from threshold cryptography and threshold signatures in particular that are dealing with kind of similar problems. Eventually we'll see a very big list of experiments that we can do today with using ECDSA for scriptless scripts. So there's no new results here, but I hope that we'll get some practical tools and I'll be able to convince you that it's secure and very much efficient to actually do it today. So in order to understand scriptless script, we need to first look at Schnorr signature. It will also be important later when we compare it to ECDSA. So it's very simple. We need to choose some random nonce k, then we compute a point, so it's a random point r, and then we need to evaluate this expression for s, which is just the addition of this nonce and some hash function that depends on the point and the message. Eventually we output some encoding of this point r and the expression s. So for scriptless, there's the shtick, which is Yiddish for devious trick, and the shtick is called adapter signatures. Okay, so this is this point t, okay, this adapter, and what we basically are doing is we are taking a Schnorr signature, or at least the s part of it, and we can write s prime, which is just the addition of this Schnorr signature to with the adapter, this little t. Now, as it turns out, using this shtick, we can achieve many of this suite of protocols that I called scriptless scripts. So I would like to start with an example. So this is kind of like the canonical example of how to do atomic swaps based on adapter signatures. So we have two wallets, wallet A and wallet B. Wallet A will fund the Bitcoin, will fund on Bitcoin, and wallet B will do a transaction on Litecoin. Both of them are a multisig of 2 out of 2, where wallet A is actually controlling the orange PKA and blue PKA, and wallet B is controlling the orange PKB and the blue PKB. And what will happen is that at first, off-chain, wallet A will send some information about the adapter, so this is public information, and the primes of his signatures in the local public key, using is known public key. Now, using this information, wallet B cannot do anything, but he can just make sure that the signatures are indeed like adapter signatures. So now wallet B will send his true signature, his true Schnorr signature to wallet A. Now, using this signature and his own signature on Litecoin for SA, wallet A can redeem this transaction from Litecoin. So he'll publish SA, and he can take this the coins from Litecoin. But publishing SA will now allow wallet B to do this computation, this shtick that I showed you, and extract T, and then using this T, you can use it to compute from SA prime, compute SA. Okay, using SA and his own known SB orange, he can now redeem from the Bitcoin. Okay, so this is atomic swap. I would have many more examples later on. This is just to give you the idea of what is mean of like an example for a scriptless script using this. Now, going back to Andrew talk 2.5 years ago, so there's a list of open questions, and we're going to focus here on this ECDSA support question. Okay, there are also other questions that are really interesting, and I'm encouraging you to look at them, because I don't think anyone did. Okay, so what are the hard questions in doing ECDSA scriptless scripts? So why? To begin with, we defined scriptless scripts using Schnorr, right? What's wrong with ECDSA? And once we clear this, we need to understand how can we actually implement it using ECDSA, because as we'll see, it's not that simple as using Schnorr. So let's look at it. So let's start by comparing ECDSA and Schnorr. Okay, so you see that they start the same. You need to compute this random point R. Then there's a line that appears in ECDSA, but do not appear in Schnorr. Right? This is to compute this little r. So what happens here is that actually a point can be defined by two coordinates, x and y, and we take the x-coordinate modulus, some public parameter of the elliptic curve. So this is a non-algebraic operation that will cause us many headaches later, and you see that this is an important difference from Schnorr. There's a few more other notable differences. One is that, as you can see, when you compute this S, so in ECDSA we are using this nonlinear term, we take the inverse of the nonce, okay? And also under the hash function, you see that in ECDSA it's just the message, while in Schnorr it's also the point R, okay? Eventually, the signatures are looking similar. It's in Schnorr, it's a point and S. In ECDSA, it's this x-coordinate modulo and S. So, let's try to understand what's the differences here, okay? So, I took this from Peter Willett talk earlier this year at Financial Cryptography, and here are the claims. So, ECDSA has no security proof and is malleable, and is not linear compared to Schnorr. So it might be that it's game over to begin with, right? So let's look, I want to look at those statements one by one and try to see what we can say about them. So let's start with the no security proof. So I'm claiming that this is not completely accurate, okay? So ECDSA has been around for many, many years, and the analysis of ECDSA has become better and better the farther we researchers have looked into it, okay? So this is an example, 16 years ago, that proved ECDSA security, but under a model called the generic room model, okay? So if you remember, Schnorr is secure under the random oracle model. Here, this is, by the way, a very popular model. It's the ZK snark in Zcash are proven secure also, is proven secure also under this model. But we are kind of missing something from the true ECDSA in reality, okay? To be specific, this line that I showed you that is non-algebraic, this is kind of something that we that's ignoring when we use the generic model. So it's, we can say that this is like not perfect. But moving forward a few years, so this is from 3 years ago, this is another paper, another example, which is proving ECDSA secure, but under now, not again the random oracle model, but a model called bijective random oracle. Okay, so now we are more close to reality, and this is another popular model, okay, SHA-3 is proven secure under this model, and as a matter of fact, this is getting us really, really close to a very good security proof, okay? Because we can already make some claims based on this security proof, as we'll see in a second when I speak about malleability, okay? So there are conclusions that we can draw from here. And what we can assume is that the more we continue to use ECDSA, the analysis will become more and more tight. So looking at the other side of the coin about ECDSA, so since it's being used so much, as you know, it's being used widely in the internet, in your email, and obviously in your favorite cryptocurrency, there's also the side of the crypto analysis, okay? So first of all, Bitcoin is kind of like a huge big bounty for finding bugs in ECDSA. And also, all crypto analytic efforts up till now has been futile, right? Nothing was found. So this might also be some argument towards the security of ECDSA. Now let's discuss about malleability. So malleability means that given a signature, we can maybe change the signature a bit to have another meaningful signature. Now there's a non-malleability in ECDSA, okay? It's very simple. If we have RNS, so and minus S will also be a valid signature. What the paper showed us, the one that I just described, is that this is the only malleability. So as a matter of fact, eliminating this type of malleability will result in strong and forgeable, which is the kind of the property that eliminates this malleability. So what we see in many recent papers is that it's just we define this ECDSA prime that fixes one of the other options, okay? So this is a way to solve this malleability that, by the way, we have, and we have a BIP 62 that is doing exactly this, is fixing ECDSA prime. And there's also, I mean, using SegWit, we kind of also dealing with the transaction malleability that also can affect this. So I would say that in terms of malleability, this is kind of manageable. Looking for a second on the other side, on Schnorr signatures, so it's true that for a given Schnorr signature, you can prove non-malleable or strong enforgeability, but in practice, Schnorr is not well standardized like ECDSA. So there are many variants of Schnorr that's supposed to be different in the verification of them, so it's supposed to be different verification to each one. But just to give you an example, so there's Bitcoin, there's BIP Schnorr, and also for Zilliqa, which is another blockchain, there's a different type of Schnorr. So this slide is taken from Stack Exchange. When someone asks what Schnorr should I use, what is the right one, the right standard for Schnorr, and someone that answered them just created this table with many, many different types of Schnorr signatures. So it's really, it can be, it's a true outcome that might be that one Schnorr would have, let's say that BIP Schnorr would have some meaning, a signature would have some meaning in another blockchain, for example. Okay. So moving on to the last point of linearity, so this is definitely a valid point. If you remember this inverse of K, this is a real issue with ECDSA that do not exist with Schnorr. And we need to ask ourselves if this is a deal breaker. Now, specifically, what I want to ask is maybe this is a deal breaker, so it's impossible to actually do scriptless scripts using, because of this non-linearity. Maybe it's possible, but it's very inefficient or inefficient in such a way that we'll prefer Schnorr. Or maybe we need to compromise on security in terms that we need to introduce new security assumptions into the equation. Okay, so observation. Threshold ECDSA kind of struggled with the same problem of linearity, okay? And it's not surprising that looking, as we'll see in a second, on existing solutions for ECDSA scriptless scripts, they are based on threshold ECDSA. So I'll explain in a second what exactly is threshold ECDSA. First, I want to mention a few of those works. So there's one work that I'll mention at the end about zero-knowledge contingent payments. This is taken from last year, Scaling Bitcoin, where like classically you can replace a multi-signature with multi-sig using this two-party ECDSA, which is a form of threshold ECDSA. And then there was, I think right before, there was a talk by Pedro that actually what they've done is that they defined scriptless script for ECDSA by constructing this adapter that I showed you before on Schnorr, but for ECDSA. And to do it, they also needed this two-party ECDSA. Okay, so what's common to both of these works and also to the third one is that both of them are relying on specific protocol by Lindell, presented at Crypto 17, for how to do two-party ECDSA. Okay, so I would like to explain about what's first, it's like in general, what's a threshold signature, because it's a two-party ECDSA is an instance of it. Then I want to explain about this specific protocol that seems to be very important. Then we'll ask ourselves our questions about whether it's efficient, secure, and should be used. And then we see how we can move forward and build on top of this and others. Okay, so to describe threshold signatures, it's two protocols. It's key generation and signing. We have two parameters, T and N, and the first protocol is this setup phase when you need to generate a key. So here, Spider-Man, Captain America, and Iron Man will collaborate, will run this joint protocol, where eventually each one of them will get a public EQ and some secret information. Okay, so you see that each one of them has secret information. Now this is three parties, but now let's say that Thanos kills Spider-Man. We still, because of the way that we designed this setup, we still are able to generate a signature to the Bitcoin blockchain by just collaborating between each two parties. So either any two parties can work together and generate this signature. Now, in Lindell two-party case, we have 2 out of 2. So we have two parties that needs to, so it's, T and N are both 2. So you need both of them to run together at the setup and both of them to run together at the signing. So looking in a very high level on what's, how the key generation here is done. So it's basically a Diffie-Hellman key exchange, where at the end, both parties agree on this public EQ. And each one of them has a secret information, X1 and X2. But then you see that there's an extra step, okay? So this extra step, I'm not going into the details of it, but basically we need to define a new, or to use a different crypto system. This is a public key crypto system that has some specific properties of homomorphism, okay? So we'll mention it in a second, but this protocol basically gives us this privacy property that there's no leakage of the secret information X1 and X2. Okay, so what can we do with it? We can sign. And how the signing is work, so how we can sign on a message M or some M prime. So we basically run another Diffie-Hellman key exchange now to get this random point R in a joint matter, and then we do this kind of computation to get this S star. So this is what I mentioned before, that this crypto system is specifically capable of doing this kind of math. But eventually, one party will send this S star, and the other party will do some more computation, and it will be able to output S and R, such that verification will succeed. And we get here that the protocol is unforgeable, meaning that each party, like a single party, no matter if it's one of them or any other party in the world, cannot forge a signature without having access to both parties at the same time. Okay, but now I needed to do this because I wanted to explain about how to do adapter signature in ECDSA. And this is how it works. So it's very, very, the change is very minimal, okay? So it's basically just, as you can see, when you are generating this random point, instead of using the generator G of the elliptic curve, we'll use just the adapter T, okay? And what it will result is that eventually the output will be S prime, which is now not an addition S plus T, it's a multiplication, such that verification is possible given that you have S prime and T, and you need to do just the inverse of T, okay? So it's similar but different. Now, what about the issues that we mentioned before? So we see that it's definitely possible to do ECDSA scriptless script because we can do this adapter signature thing, and we can, believe me, that we can build on top of it many other great protocols. What about efficiency? So we are paying by doing this setup, the key generation setup. So it might be costly. And also the signing, you saw all these computations, this homomorphic computation, it's also something that we need to pay. Also there's interaction here. What about security? So the protocol is secure, okay? But we are introducing this new crypto system and we need to have some new assumptions on the security, okay? So there still might compromise on security. So it might be again that we are in a, oh yes, and this protocol is also patented, the specific one. So it might be bad news. So I want to claim that it's not bad news because our toolbox is much, much bigger than just a single protocol, and starting from this Lindell protocol back in 2017, this is just to give you a picture of the research that was done in threshold ECDSA ever since. Of course, there were papers that were done also before that Lindell has used, but this is kind of to give you an impression of how large our toolbox. And what I want to claim is that you can just choose the right protocol for the right mission, okay? So the right use case will need the right protocol. So there are many ways to try to analyze the differences, and basically it's a work that should be done when you want to use a specific one for a given use case, but I chose a few of them. So the parameters, those T and N that I mentioned before, so you see in Lindell it's 2 out of 2, but there are many protocols that are for T out of N, for N out of N, 2 out of N. So it varies. About the assumptions, so Pilia is the assumption that we need for Lindell. This is the crypto system. It can be instantiated in other crypto systems, but this is what it shows. There are other protocols that are using other type of security assumptions, and it might be that your system is already assuming, let's say, Pilia security, so or the assumption that underlies. So it might be okay to use it. But as you can see, if you go down to the last couple of lines, and even above them, you see that we can also build threshold ECDSA without any new security assumptions on top of ECDSA, okay? What about interaction, signing ground? So there's also, again, the setup phase, but let's say that it's a one-time thing, so we can forget about it for a second. Here again, we see that Lindell might be heavy on interaction. It might be something that we want to improve, but we can, again, take a look at the last two lines. It's basically non-interactive. So ECDSA, threshold ECDSA research has gotten to the point where it's in the pre-processing model, it's true, but it's gotten to the point when you can actually do a non-interactive threshold signature even before Schnorr has gotten to this point, okay? Again, in terms of timing, it's also becoming better and better. So just to show you what's colored in green is it means that there's existing open source code that you can play with and you can use. In yellow, it means that there's going to be an open source code, okay, because those works are very new. So just to give you a concrete example, I would change the Lindell 2 out of 2 with CCL-ST 2 out of 2. This is something that was presented just a couple of weeks ago at Crypto. And there, even though it doesn't seem like there's an advantage, the whole reason of this paper was to actually improve over Lindell. So they have a killer setup phase compared to Lindell. And in terms of security, they are assuming class groups, which is different assumption. But the security proof is much more tight. Okay, so I'm not going into details, but this is like maybe one candidate that can be used. So let the experiments begin. So I want to just describe a few of those, what we can do with this type of tools. And remember, we should probably choose the right one to the right mission. So as a warm-up, of course, we can do multi-sig using threshold ECDSA. What we get here is this privacy property. Okay, we can hide an entire access structure on a single transaction that looks completely regular. The cost will also be one standard transaction, and we can go crazy with the number of parties that are involved. We can even take it further. By the way, there are links to open source code for each one of those. You can take it further and build an entire wallet out of it. So here you need to put some more cryptography into it. So it's not just the distributed key generation and distributed signing of ECDSA. You also need to have some kind of key derivation and all sorts of recovery methods, but basically it's possible. And I gave you two examples, one of us, one from Unbound. Here's an interesting one. So this is kind of a byproduct because, like, let's look at the coin join. So a coin join is basically a coordination game. Okay, so you need to somehow coordinate between, let's say, n parties to agree on inputs and outputs. There's an improvement for coin join that is Chaumian coin join that can actually achieve this kind of coordination in a more structured way. And here and also without exposing to each one of the parties that are doing the coin join what's the output of the other parties. Okay, so it's one thing to abstract it from the blockchain view, but it's another thing to also abstract it from the other participants in the coin join. And this is just using the key generation of threshold ECDSA. It's possible to also kind of structure the way that because this is basically key generation. It's a coordination game on how each one of party can generate a local view and also agree on something. So this is a really well-formed way to kind of get to this consensus between parties off-chain that can later be used, of course, without a central coordinator. So atomic swaps, as I showed you before, it can be used with the classical adapter signature, now that we have this construction for ECDSA. There's maybe one improvement because you don't need to have like a multi-sig on chain, because also the multi-sig can be now a single signature. There's another option which will not result in a perfect atomic swap, but you can do something which is a gradual release of secrets. Basically, it means that, again, if you have this kind of two secrets in each chain to each party, and you want to divide a secret and then send, let's say, a bit of the secret to the other party will send you a bit of the secret of your own secret, and then you move forward. You send one bit at a time. Of course, you need to prove that each bit that you send is actually a valid one and belongs to the secret. And there's also kind of a bias because one party will lead in one bit on the other, but it's doable and it's nice exercise. Okay, so payment channel network is built on top of atomic multi-op locks. This is the paper by Pedro that I mentioned before. So basically, you can take this construction of adapter signature and use it in a chain sort of way to get this locking mechanism. And by doing so, you can get to actually build this kind of equivalent to a hash time lock. So this is an off-chain solution for this. And finally, so this is a paper 3 years ago about zero-knowledge contingent payments, and they are pre-Lindell, so they used two-part ECDSA, which was not the Lindell one, but another one. But they are doing it, again, without script, and just to show you how it works. So we have two parties that now what's a zero-knowledge contingent payment? It's basically an atomic swap, but instead of switching one coin with another, you switch one coin with the knowledge of something. So here, Spider-Man knows X, okay? So there's some X that Spider-Man knows, and let's not, that's really important what X should be, but it's just something. So we call it the prover or the seller. He wants to sell the secret, and the verifier or buyer wants to pay for it, but in a fair way. So what will happen is that they will run this is a variant, okay? This is not the specific, this is not the specific use case, the specific thing that is described in the paper. So you run this threshold key generation, and then you generate, just the buyer will generate two transactions, like a chain of them. So one is putting the input, and then to spend it, you need to have this complicated access structure, but like very doable. And then the other transaction will be that the seller only the seller can spend, but you are actually, the input will be this threshold signature. So they are jointly signing on this transaction, and only the prover gets the signature. Then there's this magic that happens that there's a zero knowledge proof that that X is encrypted by the signature. Doesn't really matter how it happens. Then you have a broadcast, another broadcast, and you can extract. Okay, so it's really interesting and can be done today. So I'll just go very quickly in a second on like current status of research. So we are in a good position because this whole theme of threshold cryptography is in standardization process, but yet there's much to do. For example, there's some kind of underlying assumptions on the network layer, like you need to have some kind of authenticated channels. You maybe need the broadcast channels to get the thing working. We have one idea that we implemented using kind of the blockchain for the blockchain, so you can check it out. There's, of course, improvements such as accountability, how you can tell if some party cheated. There's batch signing and verification, which Schnorr excels, and ECDSA, there's also few works about it, and that's it. So to summarize, this is, I hope that you saw the threshold ECDSA is, can be used to get ECDSA scriptless scripts today without any compromise on security and in a practical manner, such that it's actually usable. So that's it.
QA, you have 3 minutes. Yes, you have 3 minutes for.
Okay, questions?
Wait until he is finished.
Yes.
Any questions?
Those questions. Yeah.
How do you think about the intellectual property about for the patent? So is there any risk to something like actually start as the ECDSA or the national? So how do you think about that?
So if I understood correctly the question, it was about interaction, and definitely there's a cost in interaction, but as we saw for specific protocols of ECDSA, we actually get to the point where you can do it completely without interaction. There's, it's a model that you kind of need to do a computation before, like offline computation, but then you can do like in a magical way without interaction. So I think that this entire thing is it really what?
IPR. Sorry, my bad pronunciation. Intellectual property.
Intellectual property.
Patents. Okay, so the question was about patents. Sorry.
Actually, the Professor Lindell founded the company, so they
Yes.
provide proprietary software.
Yes, so the Lindell protocol is patented, like one-to-one from the paper. I had a slide about it. And I think that, but I'm in touch with also the other authors, so this is the only one. Like the other papers would not get patented, at least, I mean, not according to the authors. So what I hope is that we'll have enough tools such that if there's one that you cannot use because of this IP issue, you'll just move to another one. But it's important probably to be explicit about it. So it's really hard to tell which one is patented and which not. But at least for the table that I gave, the only one that is patented is Lindell, and the rest not supposed to be.
So our next speaker is going to set up. We now have a talk by Stefano Lande, hope I'm pronouncing it correctly, on developing secure Bitcoin contracts with BitML.
We're switching. Okay. Give me a second to. Do you need the clicker? Do you need the clicker?
Yes. Hold on. I think I will do this. Just 1 second. Just a moment.
It's mine. Okay.
Yeah, okay. You want to do this? Yeah, it's the other one.
It's the other one.
Here's mine. And hold on a second.
Okay.
Something else. Something I feel like forgetting. I don't know what. That's timer? Yeah. You have 25 minutes, and then after that 5 minutes QR.
Okay.
So you'll see it go down to 0, and then 5 minutes will resume again.
Okay.
And then,
Okay. First of all, I want to say that I'm very happy to be here to present my work, which is shared with Nicola Thay and Massimo Bartoletti, which is my supervisor from the University of Cagliari, Nobuko Yoshida from the Imperial College of London, and Roberto Zunino from the University of Trento. This is not working. Okay. So first of all, I'm sure everybody here knows what a smart contract is, but very quickly we can say that a smart contract is a program that can move crypto assets, and it is executed in a decentralized fashion. So generally speaking, depending on which blockchain a smart contract is executed, we can say that we have two classes of smart contracts. Smart contract as a programs, where in blockchain like Ethereum, smart contracts are simply, let's say, programs. While in blockchain like Bitcoin, smart contracts are cryptographic protocols and a series of transactions that are appended to the blockchain to get the execution. So to support contract as a program, blockchain like Ethereum must have complex things like a virtual machine, a gas system, while contracts as a protocol blockchains can be much simpler. And this affects how we can reason about a blockchain. So, for example, Bitcoin has many more security proofs, as witnessed in many recent works. So the downside of this aspect is that programming a smart contract on Ethereum is much simpler than programming a smart contract on Bitcoin. On Ethereum, for example, you have high-level languages like Solidity and compilers from them to the bytecode of the blockchain. While on Bitcoin, you only can work with transaction and limited redeem scripts. So you have to get creative in designing cryptographic protocols that manage these transactions. So the two paradigms are also different from the viewpoint of automatic verification. In Ethereum, there are many tools that apply standard programming language techniques to verify contracts. While on Bitcoin, to prove the security of a contract, you have to build complex cryptographic proofs that are usually done by paper and pencil. So our challenge is, can we get the best of both paradigms? And more specifically, can we build an high-level language that supports automatic verification and also can be executed on Bitcoin? This slide is just to give you an idea of the complexity of current Bitcoin smart contracts. This is a very simple contract called time commitment. And a time commitment is used only as a building piece for more complicated contracts like gambling games. Roughly, it allows a player to commit, to cryptographically commit to a secret, and this player has a certain period of time to reveal the secret. Otherwise, another player gets a Bitcoin. The protocol is a piece of English prose, so it is not possible to automatically verify its security. So far, the efforts of formalizing Bitcoin smart contract have been limited to redeem scripts. We are aware of at least 3 languages for formalizing this kind of scripts. And this slide shows the first transaction of the time commitment smart contract formalizing in the languages. But that, besides formalizing redeem scripts, also can specify other parts of the transaction. So it is useful when combining together more transactions of the same smart contract. So let's say that we use this kind of languages to build a language for cryptographic protocols and use that to express Bitcoin smart contract. And we think this is not very viable because the resulting language will still be a low-level language, so it is not very easy to use. So to solve this issue, we came up with the idea of designing a 9-level language for smart contracts on Bitcoin, and we called it BitML, after Bitcoin modeling language. This slide shows the syntax of the language. So a contract can be a choice between one or more guarded contracts. And the guarded contracts have this form. You can have withdraw Alice, that sends the whole balance of the contract to Alice. Split, that splits the balance of the contract between n subcontracts that are executed concurrently. You have A:D, that means A have to authorize the contract D to proceed. After T:D, that means that the contract can proceed as D after time T has passed. Put X, that collects new transaction outputs at runtime and then proceeds as C. And finally, you have reveal, that allows to reveal some secrets. And P is a predicate that we can express on those secrets. So let's start with an example of a contract in BitML. Say that Alice wants to buy something from Bob's online store. So they handle the payment through a contract that says if Alice is satisfied with the item she bought, she sends 1 Bitcoin to Bob. Otherwise, Bob's refunds Alice. So the contract has a precondition to the stipulation that says Alice must put 1 Bitcoin to this contract. And the actual contract is this one, and it is a choice between 2 branches. On the first branches, if Alice authorizes, Bob can withdraw the Bitcoin. Otherwise, in the second branch, if Bob authorizes, then Alice can get back her Bitcoin. So it's like this condition or that one condition. So here we have a problem that if they don't agree of the outcome, they don't give the authorization, so the contract is stuck and the Bitcoin is frozen inside the contract. So to solve this issue, we can use an oracle that acts as a mediator in the contract. So we build a contract which we call escrow, that is the same contract as before, plus 2 more branches. And these branches can be activated, can be authorized unilaterally by either Alice or Bob to activate the contract resolve. And the contract resolve involves the mediator to solve the dispute between Alice and Bob. And it actually splits the balance of the contract in 2. The first one, 0.2 Bitcoin, goes to the mediator as a payment for his service. And 0.8 Bitcoins can go either to Alice or to Bob, depending on the choice of the mediator. So now, let's build the time commitment in BitML. So the time commitment requires Alice to deposit 1 Bitcoin in the contract and to commit to a secret that we call A. So the contract is a choice between 2 branches. In the first one, Alice can reveal her secret and get back her Bitcoin. In the second branch, which is active after time T has passed, Bob can get the Bitcoin. So this implements the logic of the time commitment where Alice says until time T to reveal the secret, otherwise Bob can get her deposit. BitML features a compiler from contracts to sets of Bitcoin transaction, and roughly speaking, executing a BitML contracts correspond to append some of this transaction to the blockchain. And the compiled transaction of the time commitment are very similar to the one I showed you a few slides back. And the first transaction, the init transaction, can be redeemed either by Alice with the transaction TA by revealing the secret, which is in the witness, or can be redeemed by Bob with the transaction TB after time t has passed. And note that to redeem t in it, we need the signatures of both Alice and Bob. And these signatures are exchanged during the stipulation of the contract. So before the transaction hit the blockchain. So this is such that no player can oppose to the progress of the contract after the stipulation. So the time commitment is used as a building piece for more involved contract. For example, this one. Let's build a two-player lottery in Bitcoin. The precondition of the contract requires each player to choose a secret and to deposit 2 Bitcoins as a collateral for the execution and 1 Bitcoin as a bet. The contract is a split between 3 subcontracts. One is a time commitment for Alice, the other is a time commitment for Bob, and this is the actual lottery. The actual lottery is active after both players reveal their secret, and if the secrets are equal, then Alice wins. If the secrets are different, Bob wins. So what if a player chooses to be dishonest and doesn't reveal the secret? So this contract is stuck, but the other players get 2 Bitcoin from the time commitment. So the outcome will be the same. But this contract has a problem because it is extremely unfair towards Alice. She has to guess the length of the secret of Bob, which is very unlikely. So to fix this issue and make the lottery fair, we constrained the secret of Bob, to be either 0 or 1. So in this way, any honest player has at least 50% of chance of winning the lottery. So in this case, Bob can still be dishonest and commit to a secret other than 0 or 1, let's say 42. And in this case, he will for sure win the lottery because of the probability, but he will lose the collateral in the time commitment. And so the payoff will be negative, and a rational player will choose 0 or 1. So the compiler is very handy because it saves us from the pain of uncrafting the transaction of each contract, which can be a lot. But how can we be sure that the compiler doesn't introduce security vulnerabilities after the compilation? Well, one of our main theoretical results is that our compiler is computationally sound, so we can trust the compiler. But we can trust the compiler, but can we trust the developer? As such, can we be sure that the developer doesn't make errors when designing a BitML contract? Well, the answer is no, so we devised and built an automatic verification for technique for BitML contracts. And the verification techniques can verify two kinds of properties. The first kind is contract-dependent properties that can be expressed as linear temporal logic formulas. And for example, in the time commitment, we want to be sure that eventually Bob knows the secret, otherwise Bob gets 1 Bitcoin as a compensation. And this should hold for a correct time commitment. And the other class of properties are properties that should hold in general for any contract, like, for example, the liquidity. So we say that a contract is liquid if for any possible execution there's no way that some funds remain stuck in the contract, remain frozen. So someone can always redeem the balance of the contract. And we have already seen non-liquid contracts in the wild, not in Bitcoin, but in Ethereum. The parity wallet was non-liquid from our point of view. So as an example of a non-liquid contract, let's take this one that requires both authorization of Alice and Bob to send some Bitcoins to Charlie or to send some Bitcoin to Dave. And they both have to agree on the recipient of the withdrawal. Otherwise, the contract gets stuck. So if the Alice and Bob doesn't trust each other, the contract is simply not liquid. So to make BitML useful in practice, we have built a toolchain that can be used to write, verify, and compile BitML contracts. And the toolchain is made of 3 main parts. An embedding of BitML in Racket that allows to programming BitML contracts within the .Racket IDE. A security analyzer that can check arbitrary LTL properties and the liquidity of contracts. And a compiler from BitML contract to Balzac transaction and then to standard Bitcoin transactions. To test the expressivity of the language and the performance of our tools, we have built a series of use cases that are financial contracts, arbitration contracts, and gambling games like lotteries, rock, paper, and scissors, Morra. And you can see from this table that there is a correlation between the number of players that can be 2, 3, 4, the number of transactions, and the verification time. And particularly, you can see a big jump of the number of transactions between the 2 players lottery and the 4 players lottery. And this is because we had to get creative, because we were limited by the fact that each redeem script can be maximum 520 bytes, so we had to splice the condition, the winning condition between more than one step. And so due to that, the verification time exploded. But for the other case, the verification time is a matter of seconds at most. So for every use case, the transactions are standard, so they respect the 520 bytes limit. So to conclude, I want to talk about some future development of BitML to make it more useful in practice. And we are open to any type of collaboration regarding BitML, so if you're interested, please talk to me. And we want to overcome the fact that BitML is not Bitcoin complete, so it cannot express every Bitcoin contract. For example, the participant of a contract is fixed at compile time. So relaxing these constraints and exploiting SIGhash modes, we can enable BitML to express contracts like crowdfundings, where we don't care who adds the money. Everyone can add money to a crowdfunding contract. We want to exploit relative time locks, so we can express time constraints relative to the last BitML step that was executed. And finally, we are working on a dynamic stipulation of subcontracts. That is something that will allow BitML to express payment channels. So we are currently working on executing BitML contract of chains, because in the current execution model, each BitML step corresponding to appending a transaction on the blockchain. And this doesn't scale very well, because complex contracts can require dozens of the on-chain transactions. So we want to build something like BitML layer 2, where the execution is moved off-chain, and the blockchain is used only in case of non-cooperative participant to guarantee the correctness of the execution. And finally, we would like to build BitML over Taproot. So exploiting Taproot to compile BitML, that will bring the advantages of Taproot to BitML, so namely the space efficiency that will allow BitML to be more scalable and also be more expressive, and the privacy benefits, because unexecuted branch of the scripts will remain hidden, will not hit the blockchain. So I conclude. Yes?
So why did you use Racket as your choice of language?
Because Racket is a language designed into building other language, so it seems natural to use that. I know it's a very academic language, but it works. Yes?
So you mentioned that it's a subset of Bitcoin script. Where does it stand with miniscript? Like, you can compile to miniscript?
If you are asking if BitML compiles to miniscript.
Yeah, or if it's possible. I mean, if the subsets
It is possible. For the moment, BitML compiles to Balzac because we can express all parts of the transaction, but we could also think to compile the scripts to miniscript instead of the scripting language of Balzac if maybe it is more efficient, and so we can explore this path. Yes?
Are you able to, a lot of the programs I see are very simple programs. You know, are you able to do anything more complex like stable tokens, which can be verified by, you know, just I'm curious on kind of like constructing like a stable token like MakerDAO.
Okay, so the way we build BitML is by building high-level primitives from the possibility offered by the Bitcoin blockchain. So you have to ask can you build a stable token on top of Bitcoin? So if you can do that, maybe we can also do that on BitML. If it is not doable as now, maybe it will be in the future because we can always extend BitML.
So you're limited by the underlying expressiveness of Bitcoin.
Yes, of course, because we want to be executable on Bitcoin. Yes?
So I was wondering if you could explain a little bit further how the sort of split functionality is working. That's constrained by a set of people signing. It's not actually enforced in the contract, right?
No, it is enforced in the contract because split is basically it's compiled as a multi-output transaction. So
But it has to be signed by some set of the participants.
all the transaction must be signed before the execution of the contract. Okay?
So I think we have a short 15-minute break. Please try to be back on time because we're already drifting with schedule.
Anton. Speaker is Olin Andreev. He will be speaking from Stellar. He will be speaking about ZKVM, Zero Knowledge Virtual Machine for Fast Confidential Smart Contracts.
Thank you. Okay, welcome. So what is ZKVM? Is a multi-asset blockchain architecture that combines smart contracts and confidentiality features, and it's designed to scale. It's fast, and it's written pure Rust from top to bottom. And this is the URL where you can go if you don't want to listen to this talk. Now, so the agenda is I'll explain the architecture and like what's good about it, and then I'll explain away all the trade-offs, right? So it sounds like a good plan. So what does it have to do with Bitcoin? ZKVM is a unique combination of the best ideas in the blockchain space that mostly Bitcoin developers came up with. So out of all the various diversity of ideas and cryptographic protocols, smart contract protocols, all these things, we have been picking the best things and trying to combine them in the elegant way. So in some sense, you may think about this as if you were starting Bitcoin from scratch, or if you want to travel 100 years into the future, this is how it might look like if you could put all the best that we learned in the last 5 to 7 years together. Now, how does it work? We start with the blank screen. All right. That's great. Look, it's working, right? Oh yeah, here we go. Control. Here we go. So we start with blockchain. So blockchain has transactions, and in our case, transactions are programs that manipulate value and send it from inputs to outputs. So inputs and outputs are linked. This is called UTXO model. And you can also issue assets. So it's a multi-asset blockchain for issued assets. You can do those things. So immediately, once you start with the UTXO set, you can do this cool thing, which is from Tejriya. And I will not spend a lot of time explaining how this works, but you can look it up on Google. There's excellent paper and video from MIT about that. So what's the idea? You have a bunch of UTXOs that you need to remove items from and insert items to. And you want to save this space. So in Bitcoin right now, the UTXO set consumes around 3 gigs of storage. And you can compress all of this in about 1 kilobyte. So this works by creating these Merkle trees. You don't keep the top root. You only keep the roots of the perfectly balanced binary trees. And whenever you delete the item, you have to show the Merkle proof. And the Merkle proof by itself sort of reconstructs the missing portions of the tree. So you could do a bunch of insertions and deletions and then reorganize the tree in the normal form. So this allows you to always keep the state pretty compact. Now there are a couple of pros and cons. The storage is now virtually free. You just spend like 1 kilobyte or 2 for those roots. And this means that more nodes can be full nodes. So effectively, you can package up this whole system as a library and embed it directly inside your application, not worry about having dedicated kind of storage layer. You can just dump this whole UTXO state on the disk without using any fancy database. If you just need to track the blockchain and not keep some accounting and stuff like that. The cons are obviously that you now have to provide the proofs, which means that you have to track the changes to the blockchain and update your proofs if you're a wallet. But again, if more nodes can be doing that, then it's not such a big deal. Plus, those proofs impose extra bandwidth overhead, but hopefully it could be done. It could be minimized with additional caching of the most recent items. So there's more research that you can look up by Googling UTXO about that. So that's not so bad, and you get free storage. Also, it significantly simplifies the protocol because you no longer have to think about, let's consolidate UTXOs, let's not pollute the blockchain state. Now you can use as much state as you want because only the actual users of the storage pay for that storage. They have to track the proofs and store those items in their nodes. Next, so as I said, transaction is mostly a program. So unlike Bitcoin, you don't have a hierarchical data structure that has inputs, outputs, some other fields. And the programs are localized inside the inputs or the outputs. Instead, there's just one flat program, and this was done originally with TXVM, the work with Dan Robinson, Keith Raddick, me, and Bob Glickstein at Chain a couple of years ago. And so ZKVM is sort of evolution of that approach with confidentiality. The second thing is the ZK proof, which is a bulletproof single aggregated proof in the transaction. So what does it have to do with the VM? Whenever you want to verify a transaction, you instantiate a transient VM. This is similar to how you verify Bitcoin transactions, except you don't instantiate the VM for each input, you instantiate it for the whole transaction. But it's still stateless, so this VM is checking this particular transaction in full isolation from the rest of the blockchain state, and then you throw it away. So it doesn't interact in a complicated manner with some other parts of the blockchain state. So you instantiate the VM and you run the program. And the program consists of a high-level, non-Turing complete instruction set that is aimed at enforcing the network rules. So whenever you say, I claim that this money exists, the VM will make sure that this claim is actually correct. And also allows you some flexibility in terms of adding additional constraints inside your contracts. So this is how you can compose your own custom protocols inside this thing. This is a stack machine like in Bitcoin, so things are being changed on the stack. And then while the program is executing, it records two kinds of side effects in two arrays. So one is the constraint system. This is the bulletproof's rank 1 constraint system. And whenever you execute instructions on the VM, it automatically arithmetizes the constraints and adds them to the constraint system. So this covers both the network rules, such as the amounts on inputs must balance with amounts on outputs, but also applies to any custom zero-knowledge constraints that your contracts may want to add. Once the VM finished executing, the constraint system is verified with a single aggregated proof. Finally, the changes to the blockchain state are recorded separately in the transaction log, which is effectively just a list of inputs and outputs. And once you have this valid transaction, you take this transaction log and apply it to the blockchain state. This is where you interact with the UTXO. So you could, again, fail the transaction if some output was already spent. But this is a pretty cheap operation. So all the expensive checks were done in full isolation, which allows you to verify all these transactions in parallel, which is similar to Bitcoin. Now, let's dive into what the UTXO actually is. So this is a generalization of what the output in Bitcoin is. So if you recall, in Bitcoin, the output is effectively a script and a value. So the script sort of protects the value. So you have to satisfy the script in order to unlock the value. This is the same idea here, but you have an extended version of like what does this script or predicate means, and you can store multiple items. So you can store one value, two values, or you can store some pure data parameters that are not the value, not the money, but some strings or numbers. And the UTXO set consists of those frozen contracts. So whenever you try to spend one, you sort of rehydrate it inside the VM and then have to interact with this contract. So how do you do that? You could take the predicate as a public key and satisfy it with a signature. So you can sign the whole transaction, or you can sign a subprogram as a sort of delegation pattern. And once you've satisfied this predicate with a signature, it unlocks the items and puts them on the stack so you could use them. Also, the predicate can commit to a program itself, and then you have to run the program, and then program takes care of the items and then decides what to do with them. So this gives you some flexibility. So how does it work? Well, we use Taproot. It's pretty much the same as the original idea, except it's implemented specifically for the system in Rust. But semantically, it's pretty much the same. So you have a commitment to a key with which you can sign, and you can have a commitment to a Merkle tree of different program options. So you can use both, or you can use just one of those. So if, for instance, you just want to sign, you can ignore the second part. If you want to always trigger some pre-arranged program, then you can simply set K to some unsignable key with an orthogonal generator. So you can learn about Taproot everywhere else, so we'll not dive much into that. So this is the instruction set of ZKVM. You can see that it has this pretty high-level operation. So just a few of the instructions to manipulate items on the stack, a bunch of arithmetic and logical operations to manipulate constraints. I'll talk about them in a few moments. Operations to issue and retire and mix values, and operations for the contracts. So you can unlock the contracts with a signature or executing the program, and you can also claim the input or create an output. So what's interesting about that is it's a pretty small instruction set for the features that it gives you. So original Bitcoin script is pretty big. It's like 88 instructions. Ethereum is also pretty big. Mini script is pretty small, which is pretty cool. And ZKVM is on the same like order of compactness. So the interesting part now left to discuss is the constraints. Oh yeah, one more thing I failed to mention is that values are first-class citizens. So you don't model them as entries in some virtual database tables inside the VM. Instead, the value is the actual thing. It's like a linear type that you can move around, split, and merge, but you cannot duplicate. So to implement all the cryptography around constraints, we have this awesome cryptography stack that starts with a very strong foundation. We use the pure Rust implementation of curve 25519 DALEC, which is a different curve from the Bitcoin SEC 256 K1 curve. And the reason why we use this curve is because it allows us to parallelize operations right at the CMD instruction level. So this gives us tremendous speed improvement at the level of doing the most basic cryptographic operations. Unfortunately, this curve is not a prime order curve like Bitcoin one, so it doesn't give you immediately the good abstraction. So we built the Ristretto 255, and you can learn about this from various talks by Henry de Valence, who was working on this stuff. So this gives you the safe prime order group, and anyone who is using the curve to 5519 and not using Ristretto is doing it wrong, period. Finally, on top of Ristretto 255, we build our implementation of bulletproofs that covers range-proof functionality, range-proof MPC, but those are not used in ZKVM because we use the rank 1 constraint system API that is currently experimental, and it's also coming with an extra twist to the original bulletproofs protocol that allows you to squeeze the Fiat-Shamir challenges in the middle of constructing the constraint system. So some of the weights in your constraint system can be actually random challenges when you commit to some portion of variables first, squeeze the challenges, then create more variables later. This allows us to have much more compact shuffle gadgets that just implemented in linear time, which is important for the Cloak protocol. So Cloak is a separate small protocol that performs the merge and split of multiple assets. So what Cloak does is that sum of inputs equals sum of outputs, and per each asset type, the balances are respected, so you cannot transmute one asset into another. And this is fully obfuscating the asset flow within one transaction. So this is the cloak protocol on top of bulletproofs. And in parallel with that, we have custom constraints, kind of high-level constraints API in ZKVM that allows you to build arithmetic expressions and logical expressions out of those, and automatically arithmetize and compile into the bulletproofs on the fly. So the constraints API allows you to have your custom constraints right inside the contracts. Finally, the interface to all of that cryptography is through the ZKVM instruction set. And then on top of that, you can build your own custom protocol. So the whole system is optimized for typical kind of financial use cases, multi-party vaults, payment channels, order books, stuff like that. And the cool part is that this entire stack is written in pure Rust, so when it's compiled in one single thing, it's pretty efficient, and APIs are pretty nice and clean. Of course, in your protocol, you can jump through the C ABI or just continue building in Rust, which is recommended. Now, how do constraints work? So you have ability to express arithmetic expressions and Boolean formulas, and they're expressed in kind of typical kind of fourth-like notation. So you can multiply things, you can add things, check that some things are equal, and then build the Boolean expressions. What happens behind the scenes is the VM does not really compute anything when this happens. Instead, it sort of assembles this abstract syntax tree on the fly, and what is kept on the stack is this high-level object called expression or constraint. So those instructions combine those types of objects. And when you say, I want to verify this, then it takes the final top kind of root of this syntax tree and arithmetizes it and it kind of inserts into the constraint system. And this happens pretty fast, so it can be done on the fly. So there is no specific setup, and any custom contract can do this while the transaction is being verified. So let's see how it might work. So let's say you want to have a contract that checks that some payment is made and payment has to satisfy a certain formula. And of course, all the parameters in this formula must be kept confidential. And then it unlocks the value. So what you do, you start with creating a variable out of some Peterson commitment, using this variable to construct a bunch of constraints and verify them. And then once you're sure that VM will make sure that those constraints are respected, you use this variable to borrow the value of the specific amount and type that you're interested in and create a payment to the address where you require it to be made. So notice this is like an imperative thing happening here. We do not receive a value and inspect it. Instead, we just borrow it at 0 interest rate and send it to the output. The borrow instruction also outputs the second value, which is a negative amount, which is not portable. So you cannot lock it out in some other contract. You have to deal with it. And the only way to deal with this negative value is to mix it with others in the cloak. So you have this imperative operation in your contract saying, I want this payment to be done, and then I leave this negative V on the stack. So the user has to find the appropriate amount to compensate with when they complete the transaction. Right? So this is how it looks like. So to reiterate, what we have here is a sort of an object capability system with linear types that allows us to imperatively and directly express our requirements without having like a roundabout code. So the code really expresses what we want to do. And this allows us to entirely avoid bugs like confused deputy problem, because we're not doing any reflection or any inspection during the execution. We just literally do the things that we need to do. So let's get to the fun part where we have some trade-offs, and we'll see why we do those trade-offs. So first of all, the VM is not Turing complete. So it's optimized for financial uses, and to borrow from Gregory Maxwell, the blockchain is a court. So we try to minimize any computation on chain. In the happy case, the transactions look boringly similar. They just claim some inputs, create some outputs, and you only see some signatures. and the zero-knowledge proof of the single CLO construction. So there is really not much happening in the transaction. And occasionally, when parties to a contract, like parties to a payment channel, do not cooperate, then they reveal some conditions and VM enforces them. So this covers all the usual use cases, and it's explicitly not designed for arbitrary decentralized computation. So that's one trade-off. Second is that even though we have pretty efficient cryptography and compression of the blockchain state, the amount of data that you have to catch up with is still linear. So it's similar to Bitcoin. If you want to catch up with the blockchain, you have to get all the blocks. The known ways for us to compress this amount of data, like the Coda protocol, for instance, does, uses entirely different cryptography and more interesting assumptions, which we don't do in ZKVM. On the bright side, the SPV clients can only have sort of like block headers and a little bit of kind of pieces of the UTXO set, completely discarding and not verifying the transactions, which is what they need to keep track of the UTXO proofs. So if you're sort of a light client that has a payment channel and you want to watch the status of your channel, whether it's closed forcefully by the counterparty or just to update the proofs, you need to transmit one amount of data, but this will be reduced compared to the full transaction, so you don't need to verify all transactions. Also, if you have a trusted source, there is a standard way to bootstrap the entire state of the system, because UTXO automatically gives you this commitment to the entire state at each block. So if you have this trusted source, you don't have to replay all the blocks from the beginning of times. And finally, about privacy. So what is private and what is not private in the system? So the asset types that we call flavors are private. The asset quantities are also private. The data parameters that you keep in your contracts, if that makes sense to keep them private, because you can always make them explicitly public in case of, for instance, an order book. Those can be also made private. And anything that happens within a transaction, if you have this one giant CLO construction, the asset flow is also encrypted. So what's not private are the programs that you show. The programs are all executed in the clear text. And transaction graph. So if you zoom out, then all the transactions are explicitly linked through inputs and outputs, just like in Bitcoin. Now, why we do that? So first of all, of course, simplicity and robustness. And things like Taproot allow us to not worry about the program confidentiality, because programs are by default confidential. Only in a dispute you have to reveal one of the branches. So that's the way to approach this trade-off. On the transaction graph, looks like the alternative approach is that erase the link between inputs and outputs, such as Zcash or Monero. They impose some important kind of scalability trade-off. You have to store ever-growing linear amount of nullifiers or key images to prevent double spending. And this has nothing to do with the cryptography that they use. So Monero could be using ring signatures. Zcash may have this giant accumulator with zk-snark proofs. This doesn't matter because you still have to prove that double spend hasn't occurred, and it's done in a very simple manner. You have this set of nullifiers, and you need to check that a new nullifier is not there. So in UTXO model, it's inverted. You only have to store things that are known not to be spent. And this is much more scalable. So this is why we just don't have any transaction graph obfuscation on the layer 1. But on layer 2, you could, so to speak, layer 2, you could use coin join and think of this as a distinction between TLS and Tor. So TLS by default gives you the confidentiality between point and point. And then if you want extra anonymity, you have to do extra work. So you have to find some nodes, you have to aggregate transactions. So that's the last trade-off. So to quickly recap the performance that we get, this thing is fast. We have less than 1 millisecond to verify the output, including all the cryptographic overhead, which gives us an ample room in terms of CPU performance, so we can push it up to 1,000 transactions a second. And we, of course, aggregate all the signatures and batch verify. All the cryptography uses the same curve, so everything is pretty nice. Also, it's always fast because all these additional contracts and constraints, they are not adding more than a few % of the overhead to the range proofs that every transaction has to do to prove that numbers were not out of range and like overflowing. So you can feel free to add your custom constraints. It will not much change the picture. About the coin join. So this is the rare place where the search for better privacy is aligned with performance. So if you aggregate multiple transactions in coin join, your transaction is also going to be smaller, like marginally smaller per payment, and faster to verify. So the interests are fully aligned here. And finally, you have this free storage with UTXO. And to conclude, we have the small and pure Rust code base. These numbers show both the tests and some convenience APIs.
Okay, you seem to hold it closer.
Hello. No one can hear it?
No, everybody can hear, but it's actually quite.
It was
That's
a
weird.
new battery. Also, new battery in the iPad.
Well, you're near finishing. Okay.
I can shout louder. Sure. Yeah. So we have very little code, including the cryptography. So this is all there is, and the assumptions are pretty conservative. So we just have the ECDLP on the well-known curve, and we believe that Ketchak is good. So you can learn more about this project on this link. We have specs. We have all this kind of sub-protocols, MUSIC and UTXO and Schnorr signatures implemented in kind of like one umbrella project. Specifications and code are there, and also satellite projects with bulletproofs and Restret and Merlin. You can see the links. Well, thank you so much, and we probably have a minute for questions.
How do fees play into this?
So this all doesn't cover the kind of higher consensus layer. So this could work with federated stellar consensus, and it could work with proof of work or whatever. We're like not like there are different ways to approach that. So if you, for instance, have to have fees, then you can have a special kind of asset that plays this role and is having a certain issuance schedule, for instance, to pay fees in, or you can pay fees in arbitrary currencies to whatever validators. This is like outside of the ZKVM itself.
I mean more estimating the cost of executing the program and not having more as DDoS and not as...
Oh, yeah, I see. So it's kind of similar to Bitcoin. The cost of verifying transaction is more or less proportional to the size of transaction or size of the proof. The execution of the program is virtually like parsing data structures. So the program is short, parsing it is almost instant, and you spend most of the time verifying the proof, and you know the size of the proof up front.
How can you compare this work to the Zexi project, which uses snarks?
Yeah, so Zexi uses snarks, and it's pretty cool because it uses one-step recursion in order to break the link between custom contracts and the need to do the setup for these contracts on the chain. So the only setup that the whole network has to do is to support verifying another snark within a snark, and then they don't care about the kind of custom reference strings and custom contracts that people use. The big difference, of course, is that we don't use ZK snarks at all. So we use like standard curves, standard assumptions. But Zexi allows you to simultaneously have the customization and hiding the actual program. So if you have some logic, you can hide it in Zexi, and you cannot hide it here, only partially through the taproot.
So how does this interface with the blockchain there? Because you're like, okay, it can work with Stellar, it can work with Bitcoin, so how does that work?
Well, this is an experimental project. I work at Stellar, so we'll try to put it as a sidechain, and I mean this is being in development. But you can, it's an open source, so you can go and voice your opinions there as well.
A lot of the benefits of the UTXO is like similar to accumulators. How is it different?
So Utreexo is an accumulator. It's a pretty simple one. And that's it. So you can remove things, add things. Well, the gotchas is that you have to provide the proofs and you have to keep the proofs up to date. Was there another question somewhere? Oh, yeah. Thank you.
Our next speaker is Lloyd Fournier. He'll be speaking on scriptless lotteries on Bitcoin from oblivious transfers.
So I called the tech. Something's wrong with mics. I don't understand what. But they're just dead. So we called.
Can you?
Okay, which one is yours?
I think it's OT scriptless lotteries.
Yep.
Yeah. So can you start?
Yeah, and just leave this and then Control L.
Yeah.
Presentation mode. You're gonna have to speak really loud.
Yeah, that's just for people here. I can speak
Yeah,
loud.
just for people.
Okay, cool.
This is for broadcasting. That's more.
Yeah, no worries.
It's just something happened with the mics, so we called the tech.
Okay, cool.
Okay.
You're replacing it?
Hold on a second. Do you need a clicker?
Nah, I can just do that, I think.
Okay.
That works.
The clicker also works.
Okay, this works?
Just, hold on, yeah. So what you have is, you'll see 25-minute counter.
Okay, cool.
I'll show you.
And then,
I'll present it when there's 5 minutes.
and then, okay, we said 25, and then after that 5 minutes for QA.
Okay. Okie dokie. Ready to go. Hello, everyone.
We're having a slight technical problem with the mic, so please be quiet.
Yeah, I'm just shouting for this one. Okay. I'm Lloyd Fournier, no affiliations, I'm just some guy. There is some important piece of information in this slide is that I got the date wrong. So you're trusting a guy to tell you about cryptography, you can't get the date right, so just that's where we're starting, okay? So we're doing scriptless Bitcoin lotteries from oblivious transfer. So imagine you have a trusted party, Lloyd, who conducts lotteries between Alice and Bob. Alice and Bob send Lloyd 1 Bitcoin each, and Lloyd chooses one of them randomly to be the winner with 50-50 probability and sends them 2 Bitcoin. The goal of a lottery protocol is just to achieve the same thing, but with a cryptographic protocol. So Alice and Bob are sending messages to each other, they're sending messages to the blockchain, and we get the same security. Honest parties have at least a 50% chance of winning each time. What's scriptless? You've probably heard about this. Some people call it scriptless scripts. I don't really like that name because doesn't make any sense, but so I call it scriptless protocol. So Bitcoin has a way of specifying spending rules on coins with a language called script. Scriptless protocol doesn't use it. Instead, we use a cryptographic protocol to realize the conditions under which the coins will be spent. So when the conditions are satisfied, the constraints are satisfied, the person who's able to spend it will just somehow magically arrive at a signature at that point and be able to put it on the blockchain. Examples you can replace, like you can use, instead of object multisig, you can use threshold multi-signature scheme. You can replace hash time lock contracts with adapter signatures. You've probably seen this before, so I'll just assume you get that. But these 2 things, you pretty much can replace most of the useful stuff you can do with script. I think you can actually do all of Lightning like this, but Andrew, who came up with this adapter signature idea, said yesterday that you can't. So I don't know. Why scriptless? Scriptless protocols are more efficient and more private. No validation rules appear in the blockchain, just signatures. Signatures and public keys, that's it. That's one reason you should care about it. And the other reason is to know what you can and can't do without script. So it's just important for developing Bitcoin, for moving forward. You got to know what actually you need scripts for, what do you need opcodes for, and what don't you need them for. So lottery schemes actually use script in one of the more sophisticated ways. You saw with the BitML talk, there's quite some things going on there with lottery protocols. Here's a quote from Mike Hearn back when these lottery protocols were first being proposed. I think the multi-party lottery scheme still rates as the most advanced usage of scripts found in the wild. That was before Lightning, but it's still probably up there with the most complicated use of script. And so what we're going to be doing today is showing a lottery that doesn't use any script at all. But in general, to do lotteries without a trusted third party, you need to fairly generate randomness. The randomness chooses the winner, and you enforce the outcome on the blockchain. All previous lotteries use hash commitment coin tossing to generate the randomness, and so we're just going to go quickly through that. Manuel Blum, Turing Award Prize winner in 1981, he came up with his seminal paper, Coin Flipping by Telephone, a protocol for solving impossible problems. Everyone quickly changed it to coin tossing because it sounded better. So Alice and Bob want to flip a coin by telephone just by sending electronic messages to each other. They somehow manage to flip a coin fairly, both get a random outcome. So basic idea, Alice sends a commitment to her coin toss over to Bob. Bob sends his coin toss back. Alice reveals her coin toss. She could not have, and Bob checks it against the commitment, so she could not have changed it. And then the result is computed from both the coin tosses. Here's how hash commitment coin tossing works. This is how the Bitcoin lottery protocols do it so far. So you choose a random bit. Alice chooses a random bit. She commits to it with a hash function with some long random string, sends the commitment over. Bob sends his random bit back. And then Alice now knows the answer. Before Bob, she outputs it, then reveals her preimage to Bob. Bob checks it against the original commitment, and then outputs the same thing, hopefully, if the commitment scheme is secure and that no party aborts. The thing to make note of is that Alice learns the output first, and there's just no way to solve this problem. Well, you can sprinkle a bit of blockchain on that problem and solve it, but in this setting, there is no way to solve this problem. Alice just learns the output first. So you can imagine if this number is choosing who wins and Alice knows who wins, she may not release the preimage to say, oh, I lost, Bob. So that's the first problem that the lottery protocol is going to have to overcome. First attempt, Ido Bentov comes on Bitcoin Talk and makes this thread, and there's Satoshi Dice is a huge thing at this time, and so he's trying to come up with a way of doing it without a trusted party. Cool ideas in this thread. Ido Bentov, we can use collateral. Many of the original lottery protocols use collateral to force parties to open their commitments. So if they don't open it, they lose their collateral. But in this thread, Adam Back actually came up with the most appropriate idea for lotteries, which is just if some party doesn't do something at some point, they just lose the game. They lose all the money. So this is essentially after that our first thread, there were quite a few academic papers on it, 4 or 5, 6 maybe. But then we got a nice one that sort of succinctly crystallized the idea of hash commitment coin tossing lotteries on Bitcoin. Andrew Miller and Ido Bentov, zero collateral lotteries on Bitcoin and Ethereum. So this one, it's similar to Lightning. You have a fund transaction. You sign into it, but you've already got transaction spending from it before you put it on the blockchain. And so each transaction acts like a state that the protocol is going through. There's 3 transactions, so the funding goes down. Alice can move it to the next state by revealing her preimage, little a. And then, so she's already got that transaction signed. She needs to reveal little a to go to the next state. Then in the next state, Bob can actually take the money. If he reveals little b such that the XOR of the two, little a and little b is equal to 1 mod 2, if he can do that, he can take the money. Otherwise, he can't do anything, and he waits for a timeout, and Alice gets the money. So there's no collateral in this. It's ideally what we want. Alice and Bob put in 1 Bitcoin each, and then the winner just takes out 2 Bitcoin with probably 1/2. But the reason, this is the simplest version. This is probably the simplest script. It's really, really nice and succinct. The simplest hash commitment lottery protocol. What you can see is you've got these hash preimage reveals, but in HDLCs, if we want to make this scriptless, in HDLCs we can replace HDLCs with adapter signatures, but in this case we can't, because you're revealing you're revealing the preimages, but you're actually paying the money out on a function of the 2 preimages, right? So some predicate on the 2 preimages determines whether it can be spent. It's not just knowledge of a preimage, it's knowledge of 2 preimages and a predicate is being true on them. So this is a non-trivial use of script, and that's why it's quite interesting. We can actually do this without any script at all. That's going to get to, we want just people, Alice and Bob, paying into a 2 Bitcoin transaction, and then 2 Bitcoin transactions afterwards, just with signatures and public keys, no script used at all. And to do this, it's it's pretty cool, but it's pretty tricky. We're going to change the cryptographic primitive to oblivious transfer rather than hash commitment coin tossing, sort of. And so Manuel Blum also came up with this idea in 1981. So he came up with these two ways of doing random bits. One, the hash commitment, the coin tossing, not hash commitment coin, but coin tossing, and oblivious transfer. He published in his technical report. Just to give you a rough definition of oblivious transfer, Alice transmits one of n messages to Bob of Bob's choosing, but Alice doesn't learn which one she transmitted. So the receiver security is the sender doesn't know which message was sent, and the sender security is the receiver only gets one of the messages. Okay, so Alice has n messages. Bob chooses one that he wants to learn. Alice doesn't know which one. Bob learns the message, but Alice doesn't figure out which one he learned. That's the basic idea. Here's how you could get a random bit from that. Bob chooses a random bit. Alice chooses two random messages. They do an oblivious transfer. Like, let's just treat it as a black box for now. And Bob learns the message according to his bit. Then he knows the result after Alice sends her bit over. He outputs it. Then he sends the message he learned back, and Alice can look and see which message was it that he chose to learn, and outputs the same bit. Once again, if the oblivious transfer is secure and nobody aborts, they both output this random bit. Now, obviously, it's not clear how you can go from that to some kind of Bitcoin protocol to do this. But what we're going to do is we're going to do oblivious transfer of signatures. Okay, so instead of just random messages, we're going to do oblivious transfer of signatures. And this is not, so it's not quite oblivious transfer. The reason being is you can imagine if we did just replace M0 and M1 here with signatures, like what would happen is that Alice could just put one message as a signature and the other one is just garbage. Bob did the oblivious transfer. Let's say he gets the signature. Now he thinks everything's fair, but he carries on with the protocol. Alice knows that which message he got because she encoded garbage as the other one. So we can't just have oblivious transfer, vanilla oblivious transfer. We have to have some kind of verifiable oblivious transfer, where I'm going to call that oblivious signing. So Alice has a bunch of has messages. Bob chooses which one he wants signed, and Alice doesn't know which one she chose. So we're going to use oblivious signing, and we're going to use it to in this transaction scaffold. So once again, we have this fund transaction. It's the one that's signed last, and we've already signed a bunch of transaction spending from the fund transactions and transaction spending from that before it goes onto the blockchain. So we've got to choose keys securely, rogue key attacks, whatever. This is Schnorr signatures, by the way. It's all predicated on having Schnorr signatures. You could probably do it with ECDSA, but that's not this talk. You've got to sign the transaction scaffold. So once we've chosen the key securely, you've got to sign all the transactions, this abort transaction, the pick transactions. But then for the Bob win transactions, you're going to do oblivious signing. So Alice is going to sign one of the Bob win transactions over to Bob at Bob's choosing, but Alice doesn't know which one she chose to sign. And then sign and broadcast fund. The blue transactions are the ones that Alice is going to choose. So what happens is Alice will broadcast fund. Once it's got confirmation, she'll broadcast pick 0 or pick 1 according to her own bit. Then if let's say she chooses pick 0, if Bob chose to learn the signature of Bob wins 0, then Bob's won, right? So he's got a signature on that transaction. He just puts it down and takes the money from pick 0. Otherwise, with a timeout, if he doesn't do that, Alice wins. So you can see that there's 4 possible end states. 2 of them Bob wins, 2 of them Alice wins. I hope you can see that if you actually had a secure oblivious signing protocol, that each party would win 50% of the time. So that's what we want to achieve. So we want Bob to have a signature on Bob win 0, Bob win 1, but without Alice knowing which one he got a signature on. And the approach is to use adaptive signatures where Bob only knows the completion for one of them. Okay, so adaptive signatures introduced by Andrew Polstra. You've probably seen these before. I think you've even seen them today already. So now here they are in multiplicative notation instead. you have this auxiliary point, this conditional point that you add to the signing algorithm, and you multiply the nonce by it. And this means that the S value you get out at the end of the signature is missing the discrete log of the condition. So big Y is like the condition, little y is like the satisfaction of the condition. Once you know little y, you can satisfy the condition. And there's an important feature is that the signer learns little y once they see the completed signature, right? So if I give you an adapter signature and you complete with a condition big Y and you complete it with the satisfying the condition with little y, I learn little y when I see the signature on the blockchain. So once again, approach to give Alice to give Bob adapter signatures where Bob only knows completion with one of them. Well, in order to get this this idea where if adapter signature you're able to complete it if you know the discrete logarithm of the condition, well, what we need is for Bob to know a discrete logarithm of some point, but like only one of some set of points, but only one of the set of points. So a Peterson commitment is for x is in the form t is g to the x, h to the c. It's impossible to decommit to more than one value without knowing the discrete logarithm of h with respect to g. Okay. So if we instead fix c to 0 or 1, the committer can only know the discrete log of t or th inverse. Okay. So if the committer sets c to 0, then they know the discrete log of t. If they set c to 1, then they know the discrete log of th inverse. Okay? But they can only know the discrete log of one of those two. Here is now we have just put these two ideas together. This idea you can only know the decommitment for one Peterson commitment and adapter signatures. We've got this protocol. So Bob has a choice like 0 or 1. He generates a random y and commits to y with like the c being 0 to 1. Alice now creates two adapter signatures, one on t and one on th inverse. Then sends them over to Bob. Bob verifies both of them because he's got to make sure that not only the one he wants is correct, but the other one is also a valid adapter signature. So he verifies both of them and he completes one. So that's it. That's how we get oblivious signing. Now, is this secure? Okay, well, security for the sender is that if Bob complete both adapter signatures, remember, adapter signatures, you reveal the completion, you reveal the condition, the discrete log of the condition. If you can complete both of them, then we're going to learn the discrete log of t and th inverse, which means that we learn the discrete log of h, which Bob doesn't know. So that violates the assumption that the discrete log is hard. So that Alice has security in that respect. Security for the receiver, so Alice doesn't know which one he chose. It's information theoretically impossible for Alice to learn which choice Bob made because Bob just sends a random curve point over to Alice. It looks indistinguishable from random. So I came up with that. I was very happy with myself. I'm not the kind of guy who invents new cryptographic primitives very often. So I was really happy. And then I said, I'm going to call this oblivious signing. And I Googled it and I found these guys already came up with the same protocol. So if you want like a more rigorous approach to the security of this thing, it's there. But it's not so fast. We can't actually stop yet. We're almost there. But in the protocol we just saw, Alice has a secret key, and she signs over two adapter signatures on the same secret key, on her secret key. But here in our transaction scaffold, you can see both Alice and Bob have their joint signatures. Alice and Bob each have half the public key, so we can't use that algorithm by itself. We have to change it a bit. And I think these changes preserve the security that I mentioned on the slide before. So they first choose joint nonces. Like let's say that we've done this already. We've chosen our nonces correctly according to our multi-signature scheme. Along with T, Bob sends his half adapter signatures. So Bob, with his T, now can create half adapter signatures, send them over to Alice. Alice calculates the full adapter signatures and sends them back to Bob, and we've got the same. We've got a protocol which has equivalent security as before, but we've managed to do it like two-party on joint public keys. So, okay, that's it. We did it. just a recap on this. So now Alice posts the fund transaction. She picks one or picks 0. Bob, now if he chose the same bit as Alice, is able to take the money. Otherwise, Alice takes it. And with 50-50 probability, an honest party is going to win the lottery. That's my security claim. Okay, so summary. Lotteries were previously an example of something you needed like really complicated scripts to do. They can be done without any scripts and are actually more efficient. Like this protocol is the most efficient lottery protocol, at least in its class. And oblivious signing with Schnorr signatures is secure and efficient, at least as I've used it here. That's what I'm claiming. So here's some unsubstantiated claims. Just to end it off, to pique your interest, you can do lotteries with different odds by doing 1 of n oblivious signing rather than just 1 of 2. You can cooperatively complete the lottery in 2 on-chain transactions. So instead of, once the fund transaction is down, you can actually figure out who won off-chain, and then just the loser can just give the private key of the fund transaction to the winner, and then they've got the money in there and they can spend it. I think you can execute this cooperative protocol in a payment channel. So instead of it being a fund transaction on the blockchain, it can be like a UTXO in a state of a payment channel. And I think, this is conjecture, I think you can even do it multi-hop. So can be a guy in the middle who has a lottery on his left-hand side, a lottery on his right-hand side, and is guaranteed to lose one or win the other. Like he'll lose one and win the other. Doesn't know which one, but he can be a man in the middle, and he can even do that recursively, so you can have like many hops of that. Yeah, that's it. Questions?
So the condition where Alice wins, you have a sand timer. Can that be expedited in terms of closing, or does Alice have to wait?
Yeah, there is a cooperative protocol. Okay. So if they're cooperating, you just put the fund transaction down.
So this is just like edge case of uncooperative.
Yeah, it's just uncooperative. So like in practice, you would do the cooperative protocol. You would just have 2 on-chain transactions all finished. So yeah, it would be done pretty quickly. Yeah, there'd be no waiting. Yeah. Okay, that's it. All good. Thanks.
Our next speaker is Sergio Segura from UCL, right? Going to be talking about transaction probe, discovering Bitcoin's topology, versus via orphan transactions, right? Yeah.
Is it here or should I?
Oh yeah.
Did you send it? Yeah. So I think it's here.
If it's here, I can.
Yeah. No, it's not here yet.
I tried it. I mean, I can use this one. Oh, you said you were going to use your laptop.
Yeah.
It's okay. No. What you should take is this. Put your laptop here. This is a Genoa. Is that it? I think we might have mixed up. Hold on, let me.
Yeah, no worries.
Let me get you wired up. Put this in your pocket. No, let me do this. And this in your pocket. Okay, you're connected.
Okay, I'm there.
Hold on a second.
Are we okay?
Okay, now, hold on a second still. Yeah, that's here. Okay. Okay, so Mike, so you can use that.
If that.
No, this is for the camera.
Oh, it's for the camera. Okay.
Yeah. So
Okay,
token this. You have 25 minutes here. After that, it will reset to 5 minutes queue.
Okay. Cool. Are you gonna set it up? Yeah.
Can you hear me all? Yeah. Okay. Cool. Good afternoon, everyone. I'm Sergi, as said. I will be presenting TX probe or transaction probe, as you would like to call it, which is our technique to discover the topology of the Bitcoin network using orphan transactions. This is shared work between a bunch of awesome people from different universities, ranging from UAB to UAUC and UMD. Oh, sorry. Oh, no, that's better. Handful. So, I would like to start this talk by talking a little bit about what do we know about topology as of right now, right? Without like using TX probe or any other kind of technique to like cheat or whatever you want to call it. So when we talk about topology, there are two main things we know beforehand. And those are the nodes that are in the network and the location of them, right? At least in the reachable network. So I'm sure that most of you have seen like charts like this, where we have like a heat map of like the nodes on the different locations based on the IP of the node and so on, right? But when we talk about topology, at the end of the day, we're talking about graphs. And if we talk about graphs, there's something missing here. And that's basically the edges of the graph, right? And that's like that because the edges are hidden by design. And this actually opens like some discussion between whether these edges should be hidden or they should be not hidden, right? So if we should have an open topology or we should have a closed topology. I would like to like give some argument in favor and against to motivate like why we decided to do this kind of analysis. So first, I'm going to talk about why having a hidden topology is a good thing, and that's the approach that the core has followed. So if I'm mistaking something, just like correct me afterwards, no problem. But basically, the main reason why to have a hidden topology is because not having so would could ease the performance of several attacks in the network, right? From transaction de-anonymization to network-based attacks like Eclipse attacks. But on the other hand, the fact of having a closed topology means that there's a lot of things we don't know about the network. So we are in the close here. We're in the dark here, sorry. Basically, we don't know if the network is really decentralized. We don't know if there are supernodes in the network that may be controlling the traffic, like doing information withholding or censorship. And also we don't know if there are like parts of the network that can be easily isolated because just by like taking down a few nodes, then you can like partitionate the graph and like have all those nodes in the dark again, right? So that's basically why we decided to have some kind of network health metrics that help us know if the network where we are building our system on top of is the network we want to have or not, okay? Then, being fair, we know a little bit more by checking the code, especially the core code. So if we want to know how nodes choose peers in the network, what they do basically is they choose by default 8 outgoing connections, instead of randomly picking them from the address man. And also, there's a constraint here, which is that all those nodes shouldn't be part of the same /16 IPv4 group. Basically, so no one can control the whole view of a node, right? So you don't want someone controlling the view of your network, so you cannot like be suffering some kind of attacks. And on top of that, there's also like these 117 inbound connections that your peer can receive and so on. So that's the approach of the core, and it's also the approach of all the forks of Bitcoin these days. That's common knowledge, right? So that's all for like the motivation part, like how the network works as an overview. But as I was saying at the beginning, this technique is based on orphan transactions, and specifically it's based on transaction propagation. So we have to talk about transaction propagation as itself. We also have to talk about orphan transactions, and we have to talk about double spending transactions. So in terms of transaction propagation, how this works as of now, and before Gleb talks about RLA and like the new improvements on all this, this is a 3-step protocol. Basically, when a node receives a transaction and that transaction is validated, that transaction will go to mempool, and then eventually these transactions are going to be forwarded to the rest of the network, so all the nodes can know about them, and at some point those can be included in blocks, and like that's like the main goal of all, right? Being validated and so on. So This three-step protocol works as follows. The first thing that the node will do will be to announce the existence of a transaction to his peers. And he will do so by using this inventory message with the hash of the transaction. Then, if the node that receives this announce is interested in the transaction, he will reply with a get data message with the same hash of the transaction. So basically, it's like, hey, I have this transaction. Do you want it? Yes, I do. Right? And finally, there will be like a 2-minute window here where Alice has to reply. If she doesn't do so, then Bob will like cancel this. Otherwise, he will receive the transaction back, right? So if all goes as expected, Bob should receive the transaction at the end of all this. But have this in mind because later on, this is going to be like one of the key things that we are going to be using for TX-probe. Cool. In terms of orphan transactions, these are a specific kind of transactions. They're a little bit different from normal transactions. And as the name suggests, those are transactions where some of the ancestors of them are unknown, right? So basically, those transactions are depending from certain outputs that the node doesn't know about. So let's depict this with this picture. Let's say that our node receives one transaction, transaction B, that spends from like some outputs that are well known, that are included in the blockchain, so no problem. And then our node also receives transaction D. And that transaction D is spent from a transaction C that we don't know about, right? So upon reception of transaction D, we're going to flag this transaction as orphan. And since we don't know some of the information this transaction is trying to spend from, this transaction is not going to be stored in mempool, but it's going to be stored in the map orphan transaction pool, in the map orphan transaction or the orphan pool. I'm going to be using those undistinguishedly. And we are not going to be able to validate this transaction because we are missing some information, right? So we are not going to be forwarding this transaction to any of the nodes. Then also another important thing that we are going to be using is that if we try to offer this transaction back to that node, so the node is storing the transaction in the map orphan transaction pool, and we offer it again, he is not going to reply back. And that's really important because it's different from what they will do with normal transactions. And that's what is going to help us knowing if there's an edge between the nodes or not. Finally, double spending transactions. These are like quite straightforward, so I'm not going to spend much time here. The only thing I want to say about those is that if we have two transactions spending from the same source and we try to send those transactions to the same node, the node will accept the first one, but the node will reject any subsequent transaction, right? And that transaction is going to go to mempool if it's not an orphan transaction. Cool. So with that, we have all the building blocks we need to build a basic topology inference technique based on orphan transactions. We need two nodes, three transactions that look as follows. We have two double spending transactions, the parent transaction and the float transaction. And we also have the market transaction, which is spent from the parent and will be orphan in some cases, right? So that's a transaction that is going to do the trick. And finally, we will have an observation tool. In this case, we're using CoinScope, but you can use any kind of modified node that can connect to as much nodes as can, and can send like different kind of messages out of order and so on. So let's check how can we see if there's an edge between two nodes. The first thing we will do will be to connect our node to both of them, and we will assume that the pools are empty just for the sake of simplicity. Then we will send the parent transaction to Alice and the float transaction to Bob. And at this point, we're going to assume that the parent and the float transaction arrive to both nodes at the same time. We're going to fix it later on, but for now, just bear with me. Then those transactions are normal transactions if they are separated, so they're going to be stored in mempool. At some point, they're going to try to send those transactions between themselves, but since if you have both, you have double spending transactions here, this is going to fail. And later on, we will send the market transaction to Alice, to the same one we send the parent. That transaction is a normal transaction to Alice because she has the parent. So at some point, she will decide to send that transaction along. What happens here is that Bob doesn't have the parent, right? He has the float, which means that for Bob, this transaction is going to be an orphan transaction. So it's going to go to the orphan transaction pool. Let's see what happens in the same scenario without an edge. We do exactly the same thing. We send parent and float. Those two go to mempool. There's no edge now, so they are not going to try to send this transaction along. Then later on, we will send the marker will go to mempool, and that's basically it. So if we check the two scenarios side by side, we can see that the only difference of having an edge or not having an edge is that when we have an edge, the orphan transaction is in the pool, and when we don't have an edge, the orphan transaction is not in the pool, right? The only thing that's missing now is to ask Bob about that transaction. We will send an in message with a hash, and then if Bob replies with a get data asking back the transaction, that means that he doesn't know anything about the transaction. He has not heard about it before, so there's no edge there. On the other hand, if he doesn't reply, that means that he knows the transaction, and the only way he could have led that transaction, since we have only sent the transaction to Alice, is by Alice sending it to him, right? Remember that he doesn't have the parent, so that's, I mean, the only one that can send the transaction is like a direct peer. So that means that there's an edge. And that's really cool, but as you may be thinking right, already, it's not going to be that easy, right? Because that works with two nodes, but as long as you add a third node to the picture, this is going to break, right? So cool for a network of two nodes, useless otherwise. But I mean, at least it serves the purpose of like setting the foundation of what we want to do. So let's see why this fails with three nodes. Well, this is exactly the same story, right? Parent and flood to Alice and Bob. Those two go to mempool. Then we are going to assume here that the parent is going to be sent before the flood. Again, if you're interested in it, I have like some additional slides at the end, and we can discuss about this. But just like to make it simple. So the parent is going to go to Carol. Carol will store this in mempool again. Then at some point we will send the marker. The marker will go to mempool, to Alice mempool, later on to Carol's mempool, and finally that will go to Bob and will be stored in the map from transaction pool. Right. So if we now ask back Bob about this transaction, what we are going to learn, I mean, we're going to have like a false positive edge here because we're going to believe that Alice and Bob are directly connected. But what's happening here is that Carol is here and we don't know about her. Right? So, how can we make this work at scale? We need to achieve three properties in order to make this work. Those are the isolation property, the synchrony property, and the efficiency property. And I'm going to be focusing on these two first. I have some extra slides for this if I have time at the end. Otherwise, we can chat later if you want. So, the isolation is going to be basically that once we send some of the transactions to one node, we want to make sure that those transactions stay within that node and only within that node. And the synchrony property is basically to avoid what I was saying a few slides ago, like let's assume that both transactions go there at the same time, right? We don't want that. We don't want to like have to time the things. We want to like be sure that the transactions are going to get there and they're not going to be overlapped. So in terms of isolation, what was the main issue here? The problem was that this parent transaction that we sent to Alice was forwarded to Carol. And we don't want that. We want the parent to stay within our target node, which is this one, the one we want to learn connections about, but never go out of it, right? We don't control this node, so we may think that there's nothing we can do here, but actually there's something we can. Let's see what's going on. What's going on here is that three-step protocol I was talking about at the beginning is what's kicking off this, like this, the propagation of this transaction. So if we are able to force Alice not to send this inventory message, then all those three messages are never going to be sent, which means that the transaction is never going to be sent. So the marker transaction is never going to make it through, right? But you may ask, how can we do this? Well, we can use a rather old technique called in-blocking that was introduced, I think it was like 4 years ago by Andrew Miller and his co-authors in the others paper. That actually does that. So in a nutshell, we're going to assume that we're connected to all the nodes again, just to make it easy. But how in-blocking works is that if we send an inventory message to all the nodes in the network, or at least to the nodes that we want to prevent the propagation of transactions for, they are going to like start that timing I was telling you about at the beginning, right? That 2-minute window, and they are going to ask back that transaction. That means that if any other node tries to send an in message to them, all those in messages are going to be queued, until we deliver the information they're expecting, or until it times out, right? So that means that we have a 2-minute window where both the isolation and the synchrony property are not a problem anymore. So we can like play with these easily. Cool. So let's see a simplified version of TX-probe once the network has been in-blocked. If we start by sending the part, if we start by, sending the parent to Alice, that's gonna go to mempool. Then Alice is gonna try to like imp the parent to Carol, but she's gonna reject it because she is expecting us to send it. Then we will send the flood to Bob. That's gonna get in. That's gonna be forwarded to Carol. That's also gonna get in. If they try to share this is gonna fail because the parent is there. And then finally we will send the marker. That's gonna be propagated to you, Alice, and at some point to Carol, and storing the orphan transaction pool, right? So at this point we can see how if we ask all the network about the marker transaction, we can see how Carl has the marker transaction, so there's an edge, and Bob doesn't have the marker transaction, so there's no edge, right? So putting all this together, how TX-probe works is we have to choose a node, create the parent, the marker, and the flood transactions, in-block the network, send the flood to all connected nodes but the target, let the flood propagate, send the parent to the target, send the marker to the target, let the marker propagate, and finally request back the marker. And then we have to do this for all the nodes in the network, right? That's where the whole efficiency part comes into play. So this is like the basic thing, but normally what we will do is like try to do this in bunches of nodes. So so we can like take advantage of the size of the map of the transaction pool. We have also, we've also done some estimations in terms of cost for mainnet. So in a network of 10K nodes, that will take around like 8 hours to run. And well, this depends on like the fees and like the price of Bitcoin, right? But at the time of writing the paper, it will take us like between $20 and $30 to run the whole analysis. That can actually be, I mean, it can be reduced quite a lot because at the end of the day, you don't care about those transactions getting into the blockchain or not. So if you're able to like price it properly, you can almost like put that down to zero, but whatever. Also, we have run some data validations in testnet. So we decided not to run this in mainnet, but to run it in testnet. And in order to do so, we run 5 Bitcoin core nodes as ground truth. And our precision on recall was defined as how good could we infer the connections of our nodes, right? So basically, we ran several analyses and check what was our precision on recall. So over 40 trials and with a 95% confidence, we got around, well, 100% precision and around 94% recall. And yeah, we basically draw the graph of testnet and like run some graph analysis over it. This is just one of the examples. So here we can see how the size of these nodes represents a degree, and the color is the Lubian community unfolding algorithm. So two takeaways we can see here. One of them is that the graphs we were able to draw have higher community structure than the expected for random graphs of the same size and the same properties. And the modularity was also bigger than expected, right, or higher than expected. So one of the conclusions we can get from this is that even though the code was written in a way that was supposed to build random networks, the networks that we end up having are not as random as expected, right? And we cannot extrapolate these results to mainnet because the incentives of running a testnet node and the incentives of running a mainnet node may be different. But we can see how in some situations that may end up being different than expected. So to conclude, I would like to say that none of, well, not the simplified version of the protocol I showed, nor the full version of the protocol I showed will work in Bitcoin as of right now. We sent an early version of the paper to the core, and a few months later they decided to like patch this, so it basically cannot work. This highlights like the whole like two ideas of like whether having an open or closed topology that researchers and like core devs have. I mean, but as for what I know, it may work in other like Bitcoin forks, not in Litecoin, I guess, because they may have patched it also. But like Zcash and other ones, it may work. But this also highlights this kind of like mouse and cat gaming, where like we have like one way of saying things and they have like another way of saying things. So I guess it's like right time to see, well, to come together and decide if what we want to have is like a hidden topology by design as a goal, or what we are trying to do is to have to use a hidden topology as a mean to achieve other goals, like transaction privacy. And if that's the thing, then Erlai or Dandelion will be solutions that doesn't imply having a closed topology. So yeah, that's all for me. I will take questions now. Thank you. Yeah. Yes?
How do you realize it blocked the whole network?
Well, the thing is that you don't actually need to.
Repeat the question.
Yeah, he was asking how can we be sure that we have in-blocked the whole network. So you don't actually need to in-block the whole network. The thing is that you have to be sure that the parent transaction doesn't go out, right? So what you normally do is you in-block the nodes in your set, in the set of nodes you're trying to get the links in the round you're running, right? So the ones you're going to send the parent. So you in-block those so they are not going to like send the parent along. And then you send the float transaction to the rest of the network. So then you send the float, you let that propagate, and you don't let that get in the nodes you're trying to get the links in that round specifically. And then you send the parent. Then you flip the set and do it again and again and again. Yes?
Have you been able to compare your network topology of the Bitcoin network with like the global internet server topology? And is the global topology like more random than the Bitcoin topology?
Honestly, I haven't checked, but that's a good question, and I would like to know like how it relates. So, yeah. Yes.
How do you block the mind during execution?
Say it again.
How do you block the mind during execution? Just like retry the entire day.
I didn't get it. Sorry.
So, how does the program deal with blocks?
Yeah, that may be better.
Block the mind during execution of the program. Just retry, or just not affect at all?
You can get the mic if you want. I mean.
If the marker transaction or the parent transaction got in the blocks, does that affect your...
Oh, sorry. Yeah, that's a really good question. Sorry. So yeah, if we see that the block happened during one of our rounds, we repeat the round, because if one of the transaction gets in, then that means that all the nodes in the network are going to learn about it, right? So what we do is like, that's also why it takes way longer than we expected to run the analysis. Because we have like we can run around 3 rounds per block. So if something goes wrong, then we have feedback and we repeat the round. Yeah. Sorry about that. Yes?
Does this process scale like with the number of nodes? Like how many nodes were on testnet versus mainnet, and would it be a lot slower to run mainnet?
It scales linearly in the number of nodes, but it has one restriction that it's like it's that the current approach can only be run for around 10K nodes, and that's because you have 100 nodes in the map of a transaction pool. So if you want to, I mean, what we do is like we have like a square, and then we get like, well, we separate like all the nodes in the network in a square, and it's actually a square of like 100 by 100. So we are like flipping our sets in that square, right? The thing is that after coming up with this approach, we realized that we could improve TXprobe, but then we also realized that the core was going to patch it. So it was like, there's no point in like trying to go further if we are not going to be able to like run it. So yeah. Yes.
Do you know if this 2-minute time frame after the info message is the same across all Bitcoin implementations?
It's a core implementation. So when we were running this, we were basically focusing on core nodes. But the thing is that, yeah, for what I know, you could actually queue this kind of request. So if I send you like more than one inf message, then you're going to have like a longer time window than those 2 minutes. But to answer your question, we rule out like part of the nodes that were not core nodes.
Okay.
Yeah. Yes.
Can you talk a bit more about how your research informed those Bitcoin core PRs that you had up there? I didn't quite understand.
Well, basically, wait a sec. This first one, that's randomizing the eviction policy of the orphan transaction pool, which I haven't talked that much, but let me go to the additional part because sometimes it happens. So, no, it's not the equal. Okay, one sec. Here. So that's how the eviction policy used to work, right? And in order to make it simpler, that's how it used to work better. So basically, when you wanted to evict an orphan transaction from the pool, what they used to do was to pick a random 256 value R. First, the pool was full, right? So it was like over the 100 limit. So then they pick one random value, and then they found the orphan transaction which hash was closer to that value, and then they evict that value, right? And then if the pool was still full, they did it again and again and again until that was below the 100 limit, right? So the thing is that in the whole like efficiency part, we took advantage of this in the way that we were creating transactions in a proof of work way. So we didn't just use normal transactions. We created like a ton of transactions that which hash was below a certain threshold, right? Then what we did was like to send all those transactions to a node, and then we full all the orphan transactions of that node. And then all those transactions happen to be double spending transactions of the same parent. And since you're not checking these kind of things in the map orphan transaction pool, by just sending you one transaction, I will empty the whole map orphan transaction of your node, right? So they changed that so it's actually random. Instead of like picking one random value and evicting one transaction, they picked one random position. And then now you cannot like trick the pool like that. That's one of them. The other one, that's going to be faster. Sorry. Nope. Yeah. This other one, it's basically in-blogging. So if you don't do in-blogging, the whole technique becomes way, sorry. This whole PR, it's like to prevent in-blogging. So if you don't do in-blogging, the whole technique becomes way more complicated. Because then you have to like time all the things properly, and then some transactions can get out. You can get way more false positives. So, yeah.
Okay.
Thank you.